So it's my great pleasure to introduce Chantal Keller, who is going to be our second keynote speaker. Chantal did her PhD at École Polytechnique, working on the cooperation between interactive and automatic theorem provers. She's right now an associate professor at University Paris-Saclay, and affiliated also to the Formal Methods group, working on several topics related to type theory and verification, automated reasoning. And in particular, Chantal has led the development of SMT-COC, which is a certified checker for proof certificates produced by SAT and SMT solvers, which has been really instrumental to advance this line of research in cooperation between proof assistants and SMT solvers and automated reasoning in general, in particular between COC and SMT solvers. And today, she'll talk to us about Sniper, which is a new development in this big area, which is extending this connection. So thanks, Chantal. It's great to have you. You have the floor.
Well, thank you very much, Daniel, and thank you for inviting me. So yes, I'm going to talk about the more recent works on this vast topic. And as I said to Daniel, if you have questions, feel free to interrupt, and Daniel will report the question to me. So today I'm going to talk about automated reasoning in the area of type theory. So first, I will give a brief overview of general automation for interactive theorem provers. So there is a success story for the last 15 years now, which are called hammers. So hammers are very powerful tools with proof assistants that call in parallel many solvers, automatic solvers, in particular first-order provers, but also SMT solvers and others. And from this, they get kind of certificate which allows the hammer to provide a proof in the original proof assistant. So it's now widely used in at least 3 interactive provers, which are Isabelle Hall with Sledgehammer, Hall-Light with Holly Hammer, and Mizar with Miz Automated Reasoning. So this is a very nice success story, but I have the feeling that it works mainly for provers based on higher order logics, like the 3 provers I mentioned before. And actually, there have been attempts in provers based on type theory, and in particular in COC, with COC hammer. And it appears that the tool is not did not widespread in the COC community. And so in the last years, I wondered why it did not widespread as it did for Sledgehammer, for instance. And I tried to solve this question in order to understand how we can provide general automation for type theory, and in particular for the COC proof assistant. So in COC, there are actually many automatic tactics already. So I've listed a few of them, but there are a lot of them. So for instance, there are tactics dedicated to a theory, which are called decision procedures, like ring to decide equalities in a ring, or LIA to decide equalities or inequalities in linear integer arithmetic. There is a variant for real arithmetic. There are also tactics which perform some proof search, like a quite old one, which is called first order, but also the crush tactic from Schlipala, which performs a lot of proof search using the COC tactic mechanism, or SOTO, which is a tactic developed by, in particular, Cesare Kelchik and also Chaska, that also does proof search in COC. And then there are calls to external solvers, in particular SMT solvers and first-order provers. So in the case of SMT COC, it's actually a call to external SMT solvers, and that will give a proof that will be rechecked in COC. And there is also a plugin by Frédéric Besson called iToto, which implements an SMT solver inside COC. And for first-order provers, as I mentioned before, there is COC hammer, which call in parallel many provers and try to reconstruct a proof in Coq. So we already have a lot of automatic techniques, and then I made, with other collaborators, we made experiments to understand what were the problems with this tactic. So this is the first example of a goal. So it takes two lists, and it establishes that the length of the reversal of appending the two lists is equal to the sum of the length of the two lists. And this goal can be solved automatically using Coq hammer. So the tactic is called hammer. But then I tried to change a bit this goal, and I had just one element on top of the second list, meaning that the length will be +1. And then hammer does not work anymore. So this is the problem that I call predictability. One problem with the hammer tactic is that it's really hardly predictable. When you change one thing in the goal, it looks very similar, but then the tactic will fail. And I didn't change the theories which are used in this goal, for instance. There is nothing really new by adding an element in front of the second list, because, for instance, we were already using arithmetic to prove the first goal. So yes, it's hardly predictable, and actually hammer fails either because the prover can't find a proof, or because the proof given by the provers cannot be reconstructed in Coq. So here is a second example, this time using SMT Coq. So this is a very simple goal, which says that if I take an integer x, it's equal to say, x plus 1 or 1 plus x. So SMT Coq handles theories, in particular arithmetic, so it knows about the commutativity of plus, so it's able to prove this goal. But again, if I change it slightly, instead of using the type Z, which is the type of integers in Coq's standard library, I switch to int, which is also a type of integers, but this time in the math.comp library. Then SMT Coq will not be able to prove this goal, because it cannot relate anymore this type with the type of integers used by SMT solvers. So this is another example which is particular to type theory, I think, which is that we want to have multiple representations of the same mathematical object. So in provers based on higher order logic, there is the way data structures will be evaluated does not matter as much as in type theory. So there is no need to represent, say, integers in different ways. Whereas in Coq, since computation matters, there are many types of integers, some which are easier to reason about and some which are better for computation. And this is exactly the problem we have here. If we change the representation, SMT Coq will not work anymore. In my third example, I start with the goal at the bottom. So still, I want to prove this using the math.comp integers. And in this case, LIA, so the tactic for linear integer arithmetic, will work. It works because this tactic first applies some pre-processing step that will inject the integers in one representation and then work only on this representation. Here I have a second example. So if I come back to SMT Coq, I'm also able to prove this goal, which mixes arithmetic with the theory of equality. So it's almost the same as before. X is in Z, but on top of x plus 1 and 1 plus x, I just add the fact that we apply an uninterpreted function f. So SMT Coq is able to prove this because it's in Z. and it's talking about theories that SMT-Coq knows. But if I want to mix the two now, so if I want to prove this goal, oh, sorry, there is a typo, so here it should be int. Okay. If I want to prove this goal where which talks about int from mathcomp, but with uninterpreted functions, neither LIA or SMT will work. So LIA will not work because the pre-processing that it uses fails when there are uninterpreted function symbols, and SMT fails for the reasons that I talked before, because it doesn't know the type int. So it means that when we want to mix theory, preprocessing is uneasy. It works well as long as we stay in the integers, but if there are other function symbols, the preprocessing will not work. And as the last example, I will talk about the tactic from iToto. So it's also called SMT, but it's not the one of SMT called, it's the one of iToto. So it's, which I recall is an SMT solver written in Cycoq. So again, if I take this goal, iToto will be able to prove it because it uses nice preprocessing. But then if I change the goal and make it a Boolean goal, so in the first line, the goal is a propositional goal. It uses the polymorphic equality of Coq. But if I change it to use the equality that returns a Boolean, which is specific to the of integers, then iToto will not work. And here the problem is the mix between intuitionistic and classic chain is something which is specific to provers based on type theory, since most provers based on higher order logic use only classical logic. So to sum up, we already have a bunch of tactics, but it's very hard to predict when they will work, and it's also very hard to make them useful in various contexts. So my manifesto was I would like to have general automation in a proof assistant. I think it's better to have three aspects. The first one is predictability, which means that a user can identify the class of problem it solves. So this is related to the first example I showed. We don't know why it works in one case and why in the other, but I think that a good automatic technique may fail, okay, because we are talking about undecidable logics, so it's fine that it fails, but we should be able to predict somehow when it fails. I think it should be adaptive, so this is what we saw with the example of integers. A user can specify the logic and the mathematical object is working on, and then the automation should be adaptive to these objects. And finally, I think it should be extensible. Again, it's undecidable in general. We won't be able to have a tactic that works all the time, but sometimes we can identify a class of problems in which it may be easier to have automation, and then it would be nice that a user can add its own ideas for this class of problems. So these are the three wishes that I would like to have for general automation, and I'm trying to build automation in Coq, which would, as most as possible, try to implement them. To give you an overview, I think this can be done by a compositional approach. So on this picture represents what happens in hammers that I talked about at the beginning. So usually in hammers, you start with a goal, and there is a very big transformation, a single pass transformation that takes the goal and outputs a goal in first order logic that can be given to various provers. Then the provers are called in parallel, and if one prover finds the proof is used as an oracle to help the interactive prover solve the initial goal. So this is the way it works in a very big picture. And I think the single pass transformation is one part of the problem. In particular, this is what makes things not predictable, predictable. And the second thing which I think is a problem is the fact that the prover we try to build a proof of the original goal and not a proof of the first order goal, which would, since the transformation is a single pass transformation, it would not be possible anyway to relate the goal with the first order goal. So to solve this problem, the approach I propose is to have very fine-grained transformations, many of them, and to apply them to the goal to obtain a first-order goal. And you see in my picture that there are two paths, one on the left, one on the right, because by this I mean that there are many possibilities to transform the goal. We will see later how we do this. These transformations, in contrast with the one-pass transformation, will produce proofs, which means that in the end, the prover only needs to prove, the proof of the prover will be enough to prove the first-order goal, and this will be enough to prove the original goal, since the transformations are proof-producing. And to be very compositional, what I would like to do is to have not one of these pictures, but to build them on the fly, depending on the goal. And for this, I have on one side a bunch of transformations that I can use depending on the goal and on the provers. And I also have a bunch of backends, and I can choose one which is more appropriate depending on the goal. So this is the approach that I'm trying to implement right now. So it's work in progress. There are already first results in a plugin which, as Aniel said, is called Sniper. And here I present just two examples of results that we achieve. I will come back to this example in the end to explain how it works. So the idea of these examples is to perform proofs on lambda calculus representing using De Bruijn indices. So as usual, I have terms of this lambda calculus, which are De Bruijn indices n, or an application, or a lambda. And for instance, I define the shift function that shifts all the De Bruijn indices of a term. And during this experiment, we realized that we can already automatically prove some lemmas which are often tedious. So I give two examples here. For instance, the fact that shifting by 0 is the identity, or the fact that we can compose two shifts. And in these proofs, the proof of these lemmas, we only perform the induction, because this is something which is hardly automatized. So elim means that we perform the induction on t, and we abstract on the other variables. And then we call snipe, which is the tactic developed in Sniper, and it will solve automatically the three goals of the three cases for terms. So we already have good results, and we are trying to improve it. I will explain in the end of the talk. So the outline of the talk will be the following. I will first talk about the library of transformations that we have started to develop, and then I will explain how we can use them to achieve the whole goal. I will not talk about the library of backends. I already cited some of them at the beginning, and it's actually the backends that we are going to use. So let's start with an extensible library of logical transformations. So, as I said, we want these transformations to behave mostly like a tactic in a proof assistance. So what is a logical transformation? It's something that transforms the goal G into a goal G prime. So by goal, I mean the local hypothesis and the conclusion. So it will transform possibly all of them. And I want these transformations to provide proofs. So they will provide actually the part of the proofs saying that G prime implies G. So we are not interested in the other direction because what we want in the end is to obtain the fact that the first order goal implies the original goal. To give this piece of proof, the transformation can either be proved or be proof producing. It may output a proof each time we call it. So it's exactly like a tactic so far. We will see in the second part that we have to extend the requirements for logical transformations. So if you write something that implements this, you can plug into Sniper. But for having, I think for predictability and compositionality, we also have extra requirements. So first, the transformations must be well specified, because if we don't know what they do, we will not be able to predict what the whole tactic does. I also think that they should be very fine-grained, so they should tackle only one aspect of Cox logic. We will see examples later. They also should be as local as possible, so they should not transform all the goal all the time, but they should make very local transformations when it's possible. And I think they should be independent of one another and of backends for compositionality, because then we can compose all of them to achieve our goal. So we are working on building this library of transformations. So currently we implemented transformations for 3 categories. The first one is about inductive types, since we may target backends that do not know about inductive types. So we have a bunch of transformations that will explain what is an inductive type and what is pattern matching. I will go into more details soon. We also have transformations about going to first order logic, like dealing with higher order equalities and polymorphism. And finally, we have transformations about symbols, in particular giving meaning to constants and fixed points, but also be able to switch between types and intuitionistic and classical logic, as I showed at the beginning. So I will not detail all of them. I will only present these transformations on examples. I will just give some very simple examples. But what I want to insist on is that to implement these transformations, since they are somehow Coq tactics, we used various metaprogramming tools. So in Coq, now there are quite a bunch of metaprogramming tools. They are not listed all here, but what we use is LTAC, LTAC2, CoqLP, and MetaCoq. So we already use 4 metaprogramming tools. And actually, it's a very interesting topic because right now there is a lot of interest in metaprogramming in systems like Coq, and many attempts. And we actually found that some have advantages and drawbacks. So we use 4 of them to be able to achieve what we need to achieve. But again, this is another topic which is also a work in progress, is to have good metaprogramming tools in proof assistance. Okay, so let's go back to the transformations I will talk about. I will start with the simplest one, which is equalities, higher order equalities. So let's say I have an hypothesis, H, which is an equality between 2 functions. I can't give it to a first order prover, but here the transformation is very simple. It simply expands this equality to say that actually for all the arguments, f of the arguments is equal to g of the arguments. So this looks like a very simple transformation. It's actually not so easy to implement it already using metaprogramming in code. So I will give examples of each transformation. So suppose I give a name to the function that computes the length of a list, but in the case of lists of natural numbers, so I call it length nat. Well, the transformation will, if it sees this in the goal somewhere, it will add the new hypothesis saying that the length nat of L is for all L, the list.length of nat and L. Okay, that's an easy one. Second one about constants. So if we have somewhere in the goal something which uses a constant, it's very likely that the solver will not know about the constant. So we are going to add a new hypothesis unfolding this constant. So it's very simple unfolding. So for instance, if somewhere in the goal or in an hypothesis, I have something talking about the length of a list, well, I will add a new hypothesis unfolding what is the length of a list. Next transformation is about fixed points. So the solver may not know what a fixed point is. And in particular, in Coq, fixed points are represented using a fixed construct with a local name, which is why I call it anonymous. So again, if somewhere I find something which uses a local fixed point, then I will change it into the same formula where this local fixed point has been replaced by a name. So most of the time the name is given by the user, but it can also be a fresh name. I'll just give an example right now. If I come back to the previous slide, I had at some point the definition of list.length, and this definition is an anonymous fixed point using length prime variable with a definition that relies on this variable. And what the transformation does is to replace this anonymous variable with the actual constant list.length. Okay, so I now continue with algebraic data types. So as I said, most provers do not know about algebraic data types, so I'm going to give the meaning of them. And the first step is to add new hypotheses. So each time I encounter an inductive type, I'm going to add new hypotheses stating non-confusion, injectivity of the constructors, and generation. So again, what does it mean on an example? So if I have somewhere in the goal something talking about lists, then I will add 3 hypotheses saying what a list is. So non-confusion means that the empty list is different from a list with some head. Injectivity means that if I have 2 constructed lists, then the heads which are equal, then the heads are equal and the remaining of the list are equal. And finally, generation means that if I have a list, it must be either the empty list or a list with at least one element. So again, these are hypotheses that we add in the context in order to be able to give them to the prover. We have a slight variations on this, which is to provide them without existentials, because some backends may not be fluent with existentials. So here you see in the generation, there is an existential. So to remove it, what we do is to provide projections, which are partial functions. They will work only if the list is non-empty, but which projects the list, the head of the list and the tail of the list. And then we can rewrite the generation without existentials by saying that a list is either empty or it's a constructed list with the head of the list is the first projection, and the tail of the list is the second projection. And we have a mechanism to build these projections automatically, and if the list is empty, they will return a default value. To continue with inductive types, something we may want to remove as well is pattern matching. So here I'll give the general formula. So suppose that somewhere I have pattern matching, so I match on an expression E, and for each case of the constructors, I have a function. So what we do is to add a new hypothesis, one by case, which is quite standard. So we now say that if the expression E is one of the constructors, then all the expression will be, the match in the expression will be replaced by the function applied to the variables that are matched in the pattern. So again, to give examples, my definition of list.length says that we match the list. If it's nil, we return 0. If it's non-empty, we return the length of the tape plus 1. Well, it will give two hypotheses. One saying that for an empty list, the length is 0, and the second one that you can guess. And in this hypothesis, there is no pattern matching anymore. The last transformation I will talk about is not one that we implemented in the Sniper plugin, but it's actually an external transformation, which is called tract. So it's a work by Enzo Kranz, Tony Cousino, and Nassim Aboubi that allows to switch between various representations of similar types. So for instance, integers, as I talked in the beginning, and also between logics, intuitionistic and classical logic. And I want to emphasize this work because I think it's a very nice transformation, because it works in a lot of context, and it's also fully customizable. So it means that if the user implements its own representation of integers, it can be added to the transformation. Or if you want to switch between two representations of something else, not integers, but say real numbers, it will also work. So it's really highly customizable. So that's a very nice tactic. And if I give an example, so this tactic takes as argument the target type and the target logic. So for instance, here I have a goal which uses natural numbers because the length of a list is defined using natural numbers. And it's a proposition. Since it uses the standard Coq equality. And if I call tract on Z and bool, it will target the type Z and the Boolean logic. So now, for instance, list.length of L is still a natural number, but we will lift it into the full integers. What is interesting is on the right, list.length of T is lifted, and then we apply the plus 1, which means that the plus is the plus of Z. And so this is what we wanted. We wanted to be able to use the arithmetic in the full integers. And the second part of the transformation is that the Coq equality has been replaced by the equality, the Boolean equality. So now the goal can be seen as a goal in classical logic. Okay, but if you want to know more about this technique, you can check the web page, the tract web page, which explains how it works and how to use it. Okay, so let's continue with the second part of my talk. I will now explain how we can use all these logical transformations to make the big picture we had to transform a goal into a first order goal. So this is what I call orchestration of these transformations. So we we did first experiments, and then I will talk about work in progress. So to start experimenting, we fixed the orchestration and the backend once and for all. So it means that in the graph that I presented before, we chose one path of transformations. So it means that on any goal, we will first do the first transformation, then the second, and so on. So here there are only 4, but actually we have 15 of them. And the backend is also fixed. So we, as you can imagine, I used SMTcock, which is the plugin to use SMT solvers in Coq. And this is how we achieve the example I showed at the beginning. So now I will explain how it works behind the hood. So if you remember, we have terms of the lambda calculus. We have the shift operation. And for instance, we want to prove that shifting by 0 is the identity. So with what I've presented before, what we have to do is to tell the SMT solver that what is a term and what is the shift. And then it should be able to conclude, because there will be also, for instance, arithmetic reasoning, but this the solver can do by itself. So let's see how it works. So for terms, to interpret them, it's exactly what I've shown before on lists. Okay? The term is an inductive data type with variable, application, and abstraction. And so we add a new hypothesis stating the non-confusion of the constructor, the injectivity of the constructors, and the generation of terms. So far, it's exactly what we have done with lists. It's more interesting for shift. So shift is a function, a fixed point, which is defined as usual. So definition is not so interesting, but we do pattern matching on term. If it's a variable, we shift only if the variable is large enough, high enough in the term. If it's an application, we shift on both sides. And if it's an abstraction, we shift by one more. Okay. So how do we interpret shift with all the transformations I've showed you? So the first step is, of course, to unfold the definition of shift. So we will add in the context that shift is equal to its definition. As you see, the definition, so fixed point in Coq is a nice notation, but actually the definition uses an anonymous fixed point. So in the definition of shift, it's a fix of some function f, which is a new name, and in the definition, we use this function f. So the second step is to remove the anonymous fixed point. The second step is to remove the higher order equality, because here we have the equality between shift and a function. So we remove it, and as I said, it's simply by applying both sides to the list of arguments. So we add this for all DCT, and we have shift DCT equals the anonymous fixed point applied to DCT. So now the third step is to remove the anonymous fixed point. So we will remove the fixed point and replace each occurrence of f by the name that was given by the user, which is shift. Okay. Okay. Now we have pattern matching in this goal. So we will remove pattern matching. So now instead of having only one hypothesis, it will be split into 3 hypotheses: one for the case of variables, one for applications, and one for abstraction. And actually, in this goal, we still have one pattern matching in the case of variables, because in Coq, if is actually a pattern matching on a Boolean. So the transformation, we can apply it again and replace this pattern matching by the 2 cases, the one when it's true and one when it's false. Okay. So we are almost there. The last thing that you have to do is to, since SMTCoq uses classical logic and uses integers and not natural numbers, the final step is to use tract, as I showed before, to go to integers and classical logic. So I will present the result only on the first hypothesis. So in this hypothesis, for instance, the C is smaller than N is using natural numbers. So we want to put it into integers. And for instance, T equals var N is the Coq equality. So we want to replace it by an equality, a Boolean equality. So the transformation gives this final hypothesis in which variables DC and N are no longer natural numbers, but now we have variables which are integers, which will make the prover be able to instantiate them or to work with them. Since they come from natural numbers, we had extra hypothesis stating that they are all greater than 0. And finally, the equalities are all replaced by equalities, Boolean equalities. Okay. And what is interesting, for instance, in the last line, is that n prime plus d prime is we use the plus of integer, so it's going to be interpreted by the solver. Okay. And so we have all these transformations, so the 1-4 terms that I presented on the previous slide, and these 5 transformations here. And with this, well, Snipe will be able to solve the goal. So far, so good. So what we realized by doing these experiments is a bunch of observations. So first, I didn't present it, but I told you that I have a transformation to remove polymorphism. But you see, in this example, there is no polymorphism. So there is nothing to do about polymorphism. So actually, in the chain of transformations, there is one for polymorphism, which will take some time to perform, but here it will scan the goal and do some computation, which is useless because there is nothing to do about polymorphism. The second observation is that in this chain of transformation, we really targeted SMTCoq. So we knew we wanted to go to integers and to classical logic. And we knew that we had to remove, for instance, higher order equalities. But for instance, if you want to target other backends, they may support other things. They may support algebraic data types, for instance, in which case we don't need to say what a term is. We can only give the type. Or it may use existential quantifiers, which means that we don't, for the generation lemma, we don't need to use projections. Or it may support intuitionistic logic, for instance, like iToto does. Or it may support natural numbers and not only integers. So if a backend supports one of these, it means that the chain of transformation will do too many works. So we want to remove them. Or in contrast, the backend may not support arithmetic, in which case we would like to send also to it lemmas talking about arithmetics that it may use. So for instance, if we target first order prover, and so on. So actually, if we want to be able to be very general and to target many backends, we have to think about making it more compositional. And that's why we want to go towards this compositional extensible orchestration. So what we are working on now is not to have a fixed chain and a fixed backend, but we have these two pools of transformations and of backends. And depending on the goal, we will choose on the fly the backend and the transformation. So what we are doing now is to first choose the backend. So we will choose one prover which we think is suited for the goal. So if the goal contains arithmetic, for instance, maybe an SMT solver is a good backend because it will know about arithmetic. Or in contrast, if it does not use arithmetic, but it uses a lot of quantifiers, then the first order prover is a better backend. Okay, so we first pick the backend, and then we will pick the transformations one by one. So first, again, we look at the goal, and by looking at it, it will pick one of the transformation and apply it, which leads to a new goal. So again, we look at the new goal and we try to apply one of the transformations that seems suited for this goal. And we continue until we reach a goal which is suited for the prover. And then we hope that the prover will be able to prove this first order goal and that the whole chain will work and the goal will be proved. So to achieve this, the idea we have is to extend the requirements for logical transformations. So I said at the beginning, it's like a tactic. We transform the goal into another one and produce the proof that the second goal implies the first one. But we had two new requirements. One is that it comes with triggers stating when a transformation should be applied. And the second requirement is to provide some feedback. For instance, the list of hypotheses that will be changed or added or removed, or if it changes the conclusion. The idea here is to start with a goal, choose the backend, and then from the goal, the triggers will be used to find the first transformation to apply. Then we obtain a new goal, and on this new goal, well, again, thanks to the triggers, we can see if some transformation applies, and so on. So this is the interest of triggers. And the interest of feedback is to make this process performant, because we don't want all the time to scan all the hypotheses and the conclusion and to compute all the triggers. What we want to do is we do it first at the beginning, and then we only look at what has been changed to update the transformations that can be triggered again. So here are examples of triggers. So we can already imagine how it works since I presented some of the transformations. So for instance, for higher order equalities, we have seen that when it's useful when there is an hypothesis which contains a higher order equality. So this will be the trigger for this transformation. Each time I have an hypothesis with a higher order equality, the transformation will say, hey, you can call me on this hypothesis. Another example is, for instance, for constant or fixed points, when I have a new constant that appears somewhere, or an anonymous fixed point, then I can trigger this transformation. It's very simple for most transformations, but there are some transformations in which it starts being interesting. So, for instance, for monomorphizations, so the idea of this transformation is to apply polymorphic hypotheses to a bunch of types. So there are two cases in which we want to trigger this transformation. The first case is when there is a new polymorphic hypothesis, of course, but the second case is where there is a new type which is interesting to apply to a polymorphic hypothesis that was already present in the goal. Another example of a non-trivial trigger is for the track tactic. So we can see that we have to call it when there is a new interpreted symbol. So for instance, a natural number appears, and so we want to put it to lift it to integers. But it's not so easy because tract is a global transformation. contrary to all the other transformation, it applies to the whole goal. So it means that it should be applied at the last moment. So to achieve this, transformations also come with a priority level, because, for instance, it's always better to apply the transformation for higher order equalities before before tracks, for instance. So it makes all the process quite interesting. So what we are doing, so we are implementing this orchestrator, so which will pick and apply trigger transformations using the priority level. And it will also compute the triggers after the transformation based on the feedback that the transformation gives. And it should be done in an efficient way. And to be able to write this orchestrator, we are building a language of triggers, and we try to make it expressive enough to be able to do this, but also simple enough so that people may add their own transformations and easily express the trigger of the transformation. And also, the transformation should return feedback. So we also try to make it easy for the user to explain what the transformation did. And in the case, if it's too complex, the transformation may also not provide feedback, in which case the orchestrator will scan again the whole goal. So what we are trying to do is to pack all of this in a way that is easily extensible, because I really think that it's important to be able to add new transformations in this fine-grained transformation in this process. Before concluding, I would like to thank all my collaborators on this project who are listed here. So Valentin, Denis, Enzo, Louise, Asia, and Pierre. And to conclude, I hope that I've convinced you that in the case of type theory, having a one-step transformation does not provide good automation. And I think that the keys for general automation is to have fine-grained logical transformations, to have an orchestration of this transformation which will apply them on the fly and which is adaptive, so which can be, which depends on the goal and on the backend, and to have it extensible by the user. So thank you for your attention. And if there is already a plugin sniper which is under progress. So if you want to try it, you can look at the web page. Thank you. Yes, I can. Yes. This one?
Yeah, right. Exactly. So you have all these transformations, like, and it's quite interesting the that you get with all of this. And one thing I was wondering is you are encoding into the backend what these things means, right? Such that the backend does not need to understand them.
Yes.
But one thing I was wondering is, say, and you mentioned this briefly in the end, say that you have a backend that can understand some of these things, and by encoding them, sort of depriving the backend from reasoning natively about it, so it can be less efficient, for example. But what I was wondering is, if you were to use a backend that, for example, can reason about algebraic data types, could you use the transformation module then maybe to try to reconstruct the reason that that backend did with that? So not only to transform in the way that you show the encoding, but also maybe to reconstruct or check something that the backend does.
Yeah, that's a very good question. So, as you said, if the backend natively endorses algebraic data types, the transformation will not be used in the process. But it means that this backend should provide proofs for algebraic data types, and these proofs should be reconstructed in Coq. So in this talk, I did not talk about how to implement backends, but yes, of course, if we want to support a new backend using this, maybe the transformation can be used to generate proofs and to reconstruct proofs in Coq. Yes.
Question? Yes, just a second.
For your talk, how hard just be?
Can you hear him?
It's very low.
Hold on. Hello?
Yes, okay.
Oh.
Hello.
Theorem approver example have been used in AWS quite a
It's very hashed. I can hear only one word out of two.
Didn't understand. Okay. Now?
But ask your
No.
question and Aniel will
Oh, okay. To apply the same transformations to the theorem prover or language to extend that. For example, at AWS, we use a lot lean, and it's quite impressive the power that you get from this transformation. It would be nice to just apply them to the same theorem prover.
Okay, so I guess I heard the end of the question. The idea, I think the same process will work for any prover based on type theory, and actually also for provers based on higher order logic. So yes, it would be nice to be able to write the transformations once and for all and apply them in different provers. So currently it's written in Coq and it uses, as I said, very metaprogramming tools that are specific to Coq. So I don't think it's so easy to port them to Lean, say. But maybe with other tools that allow to transfer theorems from one another, it would be possible to get the proofs from the transformations in Coq and to replace them in Lean. I think if you want to reuse the code, this is currently the simplest method. But more generally, it would be very nice to have a way to represent these transformations and the proofs they produce in a higher level language that can be used in Coq or in Lean. I don't know if I'm clear.
Yeah, thanks. Other questions? I have another question. And you can hear me, right, Chantal?
Yes.
So when you showed in the end the orchestration of all of these things, I was wondering, are you concerned or is this something that you intend to tackle about questions of termination or confluence?
Yes, good question. So, of course, we are not really interested in confluence, I think. So, we want what we want. So, we want it to be predictable and reusable. So, it means that it should be deterministic. So, the orchestrator should always pick the same transformation at the same moment, given the same goal. So, this thing, one thing that we want. But we are not really interested in saying that if we choose another path, we will get the same first order goal. Maybe I don't see some interest, but I don't think it's useful.
I think termination is the one that you really want, right?
Yes,
Confluence
so termination,
doesn't
yes. So what we do, the orchestrator remembers what was already computed in order to avoid recomputing the same thing all the time. And for some transformations, it's easy to see that the trigger will not be triggered anymore after some steps. And for other transformation, we give them fuel so that they can't be applied too many times.
Thanks. Any final question? So I think we can now thank Chantal again. Thank you very much, Chantal. This was a really nice talk.
Thank you.
Due to the potential danger associated with this kind of transport, they are classified as safety critical systems. So thus this railway interlocking system must be before the implementation and use. There is a strong recommendation to in the railway norms to adopt the formal methods for develop and test all the railway interlocking systems. So in this context, a logical verification can be used to analyze the system safety based on a unique combination of the electrical component states. So for every input configuration, we will need to have always the system must be always reach the unstable state. So, você tem como, não tá passando não. Okay. So the railway interlocking system now are based on relay implementation. So this kind of implementation is the logic, uses a logic of the railway interlocking systems to implementing in kind of the existence of railway of computer-controlled railway interlocking systems. Relay-based systems are most implemented around the world. So signals and tornadoes are controlled based on the activation and deactivation of these kind of relays, which are like this on the picture. This is a picture of a real one. So inside of the relay, we have an electromagnetic coil. When these electromagnetic coils are electrified by some source of energy, they'll create a magnetic field that attracts the blade, and this blade make the contacts change, or open or closing the contacts. So there are two specific types of contacts. There are contacts that are normally closed and contacts that are normally opening. So this is a small example of relay diagram. With this kind of diagram, it is possible to analyze and modulate some systems or some interlocking systems. Details the behavior of each component of a system. So traditionally, these relay-based railway interlocking systems are verified by manual inspection. So this kind of verification is danger in the context of safety critical systems. So to make them improvement with, it's naturally that we have to use some verification based on formal methods and mathematical proofs, model checking verification. And it's important to notice that the transient states between the input of the system is important to take account because some transient states may cause some instability during the execution, during the performance of the system. So in this diagram, we have a problem because the P1 and P2 are the positive energy sources, and the N1 and N2 are the negative energy sources. When the button B1 is pressed, he electrifies the path between P2 and N1, causing the electrification of the relay R2 that closes the contact C2. When the contact C2 closes, the path between P1 and N1 are electrified too, and the relay R1 open the contact normally closed C1, causing the deactivation of the relay R2. So this cycle of constant activation and deactivation are dangerous in the context of relay-based interlocking system and safety critical systems because the system never will reach to a unstable state. It will always be constantly activating, deactivating, and then will cause the breakdown of the relays because the heat generated by the open and close of the relay will cause the breakdown and the system will stop to work. So CSP is a formal language designed to create and modulate some concurrent systems. Every channel in CSP has a specific type, like an integer or Boolean or even a set. These are the notations that we use to develop this model. The most simple process is the stop. This means the stop is a deadlock process because you don't do anything. It's only the empty trace. The skip are the notation that represents the termination of a process. The prefix is a notation that means perform the event A and after behave like process P. External choice is a choice between two processes that have made by the environment. Internal choice is a choice made by the system itself internally. This is the notation to put two processes in synchronism. You can put the process P parallel to process Q when they perform the event CS. Interleaving is the notation to each process perform his event freely. Hiding is the possibility to not show the events performed by the process P. And renaming is the notation to when process P perform the event B, instead B will be informed, the event A will be informed instead. To create the specification, we have made some diagrams like the first one to test and model all the components that we have used. So in the paper had a link to a web page when we show all the diagrams to validate and verify the behavior of each component. So now we'll start to talk about the specification itself. In our previous work, we tried to construct to modulate the relay-based diagrams when each component have his own process. So to put on the system to work, we used a strong parallelism synchronization. And this kind of approach lead us to an explosion of states because when we realize the model checking, we have an explosion of states. So the new strategy is to concentrate all the components into a single process, as we call path master. So the path master will keep track of the electrification of all circuit, and offer the possibility to receive the inputs of the system, evolve the status of some components like relays, evolve the time for the components that need time to be activated, like capacitors and the activation time blocks, and perform an output. This is a recursive process, and every time that one of these inputs are evolved, the state of these inputs are evolved, the process calls itself with the new parameters and starts again. To create a specification to use our approach, the final user will only interact with the problem CSP file, where the diagram will be described, and set the session that will be tested. So the general CSP file and the functions file are hidden from the end user, because these two files contains the logic behind our approach. So to set this diagram in our model, we have first name all the components with one ID, put on the connections set like this. P1 is related to R1, R1 related to C2, to describe the connections of the relay diagram. So after that, you have to put the IDs in the correct sets, like positive IDs, negative IDs, relay, contacts, normally opened, contacts normally closed, and describe the relation between the relays and his respective contacts. These are the accession file. These accessions describe the way to find the ring by effect. So you have to inform the contact that you want to be verified, and the position of the button, true for button pressed and false to button not pressed. This other verification is a contact status verification that will be detailed next. So with this kind of verification, we can attest if unwanted configuration of contacts, open or closed, is reachable on the system or not. These are all the verification that can be done on our approach. The first three are standard verification that the tool that we use, the FDR4, may realize, and those four are the verification that we developed. So applying this, the standard verification of the FDR4 to this model, we didn't find any problem. The model are not having deadlock or divergence in this deterministic system. The first test is search for some short circuit. The short circuit logic behind this test is the path master's search in the connections. If we have a path that starts on a positive energy source that leads to negative energy source without any components that consumes energy. In our approach, components that consume energy are the relays, the capacitors, the blocks, the lamps, and else. If the path master finds some path between positive and negative that don't have any one of these components, their session will fail, and in a counterexample, we will have the exactly path that causes the short circuit. The ring bar effect verification is performed in a specific contact, and we will have passed as parameter the position of the button that controls the system instead. So if the traces refinement show that the run function is a built-in function of FDR that always offer the one event pass as parameter to be performed. So this monitor is capable to take the behavior of this contact, and if this contact is constantly change position, is constantly he's performing every time the event switch. So if the contact is always performing switch, and it can be a refinement of run the switch, that is a function that always offers switch, we'll have a problem, the ring by effect problem detected, so the session fail. In this case, when the buttons are not pressed, the contacts are not changing the position every time, and cannot be a refinement of run the switch, and the session not fail. This is the function that I said before, to search some combination of contacts open or closed. This verification includes the intermediate states. So even these combinations dures for a fraction of a second, the session will accuse that, yes, it's possible to reach this combination. So after that session failed, we have to analyze if that combination is really dangerous or not. This verification is only for lamp stats, or for the lamps of the diagram. So with this verification, we can check if it's possible two different lamps be activated or deactivated, or one activated or another one deactivated at the same time. So we have to pass the set of open components, or the components that will be on or off during this activation or deactivation, and the assertion will show if it's possible these two lamps to be on, for example. In this case, it's impossible because this contact have only one position, so for the two lamps to be on at the same time, it's a bit very tough. And this test was developed because in the study case, for example, we will show you a signal, a luminous panel used to be a sign of a railway. If we have a green light and a red light on at the same time, it would be dangerous for the railway. So this is our case study. It's a real panel that still used in the French railways. This is the adaptation of the real diagram. We have to took off some components like the AC/DC transformers and the alternated AC current. So our model only deals with DC current. And as expected, when we apply our previous version to this diagram, we encounter an explosion of states and cannot perform any kind of verification. With the improvement, with the PathMaster, we can now animate this diagram on Pro-B tool that are offered by the FDR4, but we still cannot perform the verification test. So to do the verification, we try to divide the diagram in 4 parts. So this part acts like an input. There are only relays here and some contacts. So to do the verify, we take some, for example, this head part, check if the relay RPA and CA causes some problems, some deadlock, some ring by effect, or some combination of dangerous contacts. If we found some problem here, we go back to the whole circuit and then try to put the combination configuration of the row system using the Pro-B animator. If it's possible to set this configuration, yes, we have a problem. But if it's unachievable, we have a false positive. And this is the logic to do with the other parts. So this is another. And to conclude, this is our approach has created one way to use CSP to verify a relay-based railway interlocking system. We we'll keep going working on this model and try to expanding to develop some another components like lamp bulbs or AC/DC transformers to include the alternate current. We aim to create some kind of tool that can be automatically generate the model to be more user-friendly, and this is it. So, thank you.
So we have plenty of time for questions. Do you have any questions? Sergio, please.
That was very interesting work. I thought that the pictures you drew at the beginning were very small, but they were just examples.
Yeah.
And the larger one was interesting too. Did you do ones that were larger than those? Or that was the largest one you tried?
Tá ligado? Teste? No. We try with this larger one, the industrial case, but see, we tried with this larger one, the industrial case, but for each component we created another example, another diagram to test the behavior of this component. So, answer your question, the larger one was the study case.
Okay. It will be interesting to see how it performs on larger ones.
On larger ones, yes.
Yeah. And I have another question. Have you thought about this tool to make it more user-friendly? Well, that's an interesting question.
And this work is a part of my master dissertation. So if I have more time to develop this tool, it would be nice. I will try to keep this.
So it's not about a new question. Just to answer your question, in fact, this is the biggest scheme that you can have to deal with the French railways. There is nothing bigger. This is not the maximum size. Yeah.
This is the maximum.
The installation now. Quite simple. So usually, instead of having big installation, you have the functions are distributed. So you have smaller systems, and you verify the systems of that size.
Okay.
Do we have any other questions?
So in order to analyze this example, you said that you had to split, right, in 4 parts.
Yes.
But what was the logic behind this division? How do you define the boundaries? Oh, this will be one component, the other one is this one, and so on. Because I think the relationship between the different parts may also affect the analysis, right? Somehow.
Right. We can. The logic behind the test was, for example, this part here. They have only lamps, and the relays are above of them. So if you find some problem in this part, we get back to the whole figure and try to configure these states on the Pro-B animation. So if you find a problem, okay, this is a danger, but if you don't find, it will be a false positive. So we split we put the relays directly related to this context to test separately. So this is how we think to be done.
Yeah, but for instance, when you put them all together somehow, one of the scenarios that could be an issue in one of them when you compose them with other components may not be reachable, let's say, right? Because the other component controls the signal that goes to the other one, for instance, right? So I think the composition also has to be checked, right?
Checked, yes, you are right. Yes.
Any other questions? I have the last one, maybe two. So I saw that you are using a timing block. There is support for a timing block.
Yes,
I suppose
yes.
that you use ToxSP.
ToxSP, yes.
Can this be a bottleneck of your strategy in terms of scalability?
Yes, I think that one of the problems we have with scalability is the time components. So we will need to try to create a better solution to minimize the state explosions.
Okay, and a last one. When checking the ring bell effect, you were using the refinement assertion.
Yes, yes.
Have you thought about trying to use divergence checking? So you could hide a lot of events, but keep one event not hidden and try to check for divergence?
Esqueci de falar isso. So this process, monitor system state unstable contacts, is a process where I hide all the alphabet of the system. The only visible event in this process is switch. So if this monitor keeps doing switch, it will be a refinement of run the switch. And will be a refinement of run switch that always offers switch, and we don't, it is a behavior we don't want to occur. So I hide. Maybe using the diversions is a better approach.
Yeah, I don't know, because sometimes
FDR has some
for some very specific
yes.
So let's thank Paulo again.
Thank you.
And I'll try to explain why these keywords are here. After I'll give you an overview of this work, include the state of the art, and after I'll give the contribution of this work. Actually, there is another result here that I will present. And finally, I'll give you conclusions and some future directions. Here, what is the motivation? Testing. Why I put testing here, or why I work with testing? Because the test is one of the most important activity in software development. What is the idea? We want more quality on the product or on the process of developing process. And here testing, we are looking for complex system, or we aim to work with complex system. I mean real-time system, reactive system, critical system. And when you work with complex system, you need something more rigorous. In this case, we work with model-based testing approach. And when you work with model-based testing approach, you need to choose what is the formal lead behind this approach. So I put here an example, a transition system, very well known, finite state machine. I have here an state, here another state. I can move from state S to state Q with an input and output. What it means? It means I'll give an example. If you want to take some money, you insert your card in automatic teller machine, and you just see a message. Okay, your card, it's okay. So you see here that the input and output has a strong connection. But here, when I use the LTS, a level transition system, you see that we have only one action. It means sometimes this action can be an input and sometimes can be an output. That's the hard part to work with a truly reactive system. What is the idea? If I have the reactive system, I get some input from the environment, and this reactive system produce some output. And we have this communication between environment and reactive systems. So, in this case, we are focused on truly reactive system because we want to see how works when you have an air conditioner, for example, where the inputs and outputs can occur asynchronously. For example, I put this model here that is NIO-LTS, and the idea for the air conditioner is I can push the button on and it continues on, okay? But something from the environment happens. Okay. Another thing it can be occur here is temperature that is reading from the environment, and it can be many times, and in such a time the temperature reach, it's very cold, for example. Then my model says move from on to off and turn off the air conditioner. Actually, this it's done just got in a standby model and then returns to read the temperature, and if a temperature, a goal, it's reached, this turn on again. Okay, that's the idea, because we have the possibility to have asynchronous input and outputs occurring in the system. So in the context of this work, we push a little bit more, and we are working with push-down reactive system. That is a reactive system with a stack memory. It means we have a memory now to do something. I have to remember something that happens. Like here, if I put, doesn't matter how many times I put the button on. But in this case, I have the memory because the number of the inputs taken account. So I put this example. It's very simple example here, a coffee machine. I have here an input coin. So I want to buy a coffee. Actually, it could be a vending machine, it could be a drinking machine, but I put a small example, so I just buying a coffee here. I put some coins. Each time I put a coin, I have to push something, a symbol in the stack memory. After I can ask a coffee, and then if I put some coins, I must be charged. Okay, after I will charge, I must be in charge, I will get my coffee. So when I put here, this example here, I don't realize that there is a problem here. If something you can identify, there is a problem here. No, nobody. If I want to buy a coffee here, maybe I will not be possible to do. So, what? No? Okay. If I put one coin, and after I push the button to order my cough. I move from S0 to S1, and here I will charge 1 coin, and here I will stuck. In this case, I don't get my cough. But okay, I realized it after, and I left it in this way. Well, what I have to say here, of course, it's a reactive system, so we have input and outputs. And what else we have here is a partition between some kinds of actions, like call. What is call is an action that when it happens, I push something in the memory. We have an internal action. When it happens, the stack remains unchanged. And I have here an action, return action. When we have a return action, this return action will pop something from the stack. That's the idea for this model. Well, now I recall the model-based testing because model-based testing is very large. We have so many subjects here, and my focus is on conformance checking. What is the idea? If I put the stimulus for the system, I put in the implementation of the system, I put this stimuli for the specification, and I compare the output. That's the idea for conformance, the general idea. Well, the question is, does the implementation conform to a given specification? In this way, I put more details. I put here 2 inputs and 2 outputs, because the question is, what is conformance here? I have to define what kind of conformance I want. So if I put 2 inputs and 2 outputs, I give a sequence of events that can communicate with the system and with the specification. And for example, for this input, I have A, B, and after I have here an output X, and it's equal. The behavior is the same. After I have A, B, A, and Y, and the behavior is the same. And after I have NA, but here the output is Y, and here the output is X. Of course, the behavior is different. In this case, I said, no, the implementation does not conform to the specification. What is this kind of conformation? Is, in a high level, the yoke relation. Yoke relation is a classical relation from the literature. And as I said before, I have some results in other works. So I have a language-based conformance, but in this case for a simple language using regular language, where the idea is I have sets of set D and set F, one to desirable behavior and another one for specifying undesirable behaviors. In this context, we are looking for reactive system, not push-down reactive system. So what is the idea for language-based? I have an input. I have to stimulate the implementation and the specification. If my input is an input for the language, the desirable language, so this desirable language is in the implementation, it must be in the specification. That's the idea. What is desired, I must to confirm in the implementation and the specification. If I take default language or undesirable behaviors, this desirable behavior can be here in the implementation, but I cannot check this behavior in the specification. That's the main idea or the big picture for the language page conformance. So what we have so far, or the state of the art, we have conformance for reactive system using IOLTS models. Here, from the literature, you have IOCO. We have a little bit more with regular language. Now I'm working with push-down reactive system, and we have here an IOC-like. It was inspired when IOC conformance. This push-down reactive system, we have proposed a new model to capture this idea. And now in this work, we are working with visibly push-down language to specify desirable and undesirable behaviors. So what is the contribution? We are with a complex system here, push-down reactive system. We have a static memory to deal with. We have proposed a new conformance checking for this new model. Here we can specify some properties that they are desirable or undesirable behavior using VPLs. VPL are visibly pushing down language. What is it? What is it? VPL is a proper subset of context-free language. Why it is a proper subset? Because we have that partition between calls and returns. So we have more ability to deal with. But VPL is a proper subset of regular language. In this way, we have, of course, an improvement here when in a past step we have regular language. Now we are working with visibly pushing down language. So what is the condition and why this condition works? Well, we give two languages, a desirable and fault model. We give a specification and implementation. What we have proved is an implementation conforms to a given specification according to D and F, both languages. If and only if this condition is checked. What is this condition? This part here is a test suite or complete test suite. And you can see here it's a peer, an implementation. We can split in both paths, in two paths here. If you put the implementation, we are considering that you know the structure of the implementation. If you doesn't consider the implementation, you don't know, we are working in a black box testing. So here we are working in a white box testing. So we have to consider this condition and check if it works. That's the idea. So to do so, we have done here, we had related IOVTS with VPAs. We guarantee that no remove, non-block, non-deterministic properties are present in a VPA. And we have proved some closure props like intersection, union, and complementation for VPLs. So we proposed and we describe an algorithm that the idea is to find a balanced run, balanced because we have to count now VPL has this characteristic to find some balance between words. And the idea is to find this witness. If we find a witness, so the condition is not empty, I mean the set of words that are here in this model is not empty, so we say the implementation does not conform to the specification according to the DF language. The idea is we have a whole model for this condition. We have a whole model for this condition, a VPA, and I have to search in this VPA this witness. I start in a configuration from the initial state, and I go to a final state with a final configuration. If I find this, so I have a witness fault case. I put, okay, there is time to see an example. I put here 2 input symbols, 1 output symbol, 1 call, 2 returns, and there is no internal action. And we have only 1 stack symbol. Let's see, the specification is this, is like a balancing language. We have here A, and a push the big A. I can go from S0 to S1 with B. It means I have to pop the big A. The idea is to have something like the number of A's is equal to the number of B's. What is the difference from the implementation? It's just this transition from 2 to 1 with the X that is return with the bottom. Okay? Just a little bit different here. If I get a desirable behavior, like I said, it's a balance between A's and B, terminated with an X, and a fault model, a fault language will be a number of A, and we have just 1 more B in this case. The question is, my implementation conforms to the specification according to the sets of D and F. So here, of course, we can go to the models to check, but believe me, it's fine. Well, I can see that the fault language is not a subset of S, so we have the intersection between F and S is empty, so we have to reduce the test suite for D intersection to the complementation of S. Here we can construct a complementation of S and see that the language D is a subset of the complementation of S. If you take an example, take AABBX, and we see that AABBX belongs to D, and AABBX belongs to the implementation. That's, we have a witness. So the implementation does not conform to S according to D and F. If we back here, oh, sorry, we back here, we can see, we can put or push 2 A's on stack. After, I can do this transition with B and this transition with B. But there is no transition with X. Here in the implementation, we have the same A, B, B, but we have this transition with X and button. That's why here we have this answer. The implementation does not conform to the specification. Now, let's take isomorphic implementation. What is isomorphic? It's the same machine, it's the same model. Here, I put again both models, and this in red, you cut out, okay? It's an isomorphic model. Well, if I take the same behavior, A, B, B, X, we see that these not belong to the implementation, and so the condition is empty. It's expected because if we have this condition empty, so the implementation conforms to the specification. Note, we have take here isomorphic model. So that's okay. But now, let's assume another fault language like A plus and X. We can see that F, this language, this undesirable language, is a subset of S, so D is a subset of the complementation, and we reduce the test suite to D union with F. Again, if we take the same behavior, AABX, nothing changed, and the answer would be, okay, considering the desirable behavior, the implementation conforms to the specification. But if you try another word like AAX from the default language, we have here AAX in the implementation, AAX does not belong to D, and AAX, of course, belongs to F. Since we have reduced the test suite for D union with F, we have this condition does not hold. So we have here that the implementation does not conform to S, even if they are isomorphic. It's a bit weird, but we see we have here a fault language. I said what I have to consider fault. So the yoke relation or yoke-like relations do not find such kind of faults. That's this approach can find this fault. Well, to conclude, we have treated here a more complex pushing down reactive system. We consider that they have a static memory that it's hard to deal with. We are not aware another approach that work with pushing down reactive system and conformance testing. We have used VPLs to define these sets of desirable and undesirable behavior. We have defined a new conformance relation based on VPLs. We have provided this method for checking conformance, and we have the algorithm and construction in a polynomial time complexity. Well, to finish, some filter directions. We are currently working on an implementation. Actually, I have an implementation in Python, but it's very simple, without any interface, without any facility. So I have to describe my models in a text file. It's very hard to do. So I intend to improve this tool to be more user-friendly. And also you have to test more practical application, bigger specification, and so. Thank you. That's it.
Do we have any questions? I have some, but I will cut in short due to the time. Can you go back to your definition of conformance, please?
The condition.
Yes.
Here.
You say that you proved that tconf is equal to that. Is this a proof or is this a definition?
No, it's a proof. a lot of lines of proof.
So you have a definition of what is conformance.
Yes.
And then you prove that your definition is equivalent to this expression.
Yeah, that's it.
Right.
But
So
of course, I miss here because in the presentation,
sure.
proof is not so good.
I just missed the definition itself. But okay.
Yeah.
Second question, your conformance relation relies on a notion of final states, is this right?
LTS, but in this case, we have stack memory we call by IO VPTS.
Okay, I'm asking because IOCO originally is not based on any notion of final state.
Yes, it is.
Sure.
Yeah.
Okay, you can see.
Okay, you can see, but I'm quite sure.
Concerning IOCO, the definition is for any trace of the specification, the set of outputs of the implementation is the subset of the outputs of the specification. So this expression is to hold for any possible trace of the specification. And I think that in your case, when you define that language where the number of A's is equal to the number of B's, this only holds on some particular states of your...
Here?
Yes. But we can elaborate this further due to the time.
Okay.
And a last comment, have you considered modeling the environment? Because there are some variations of IOCO where besides modeling the specification, you also model the environment, so that when you are testing for conformance, you combine both the implementation and the environment.
Yes, I think it's a good idea when you work, it's a good idea if you are working in a black box testing, if you don't have the implementation. Maybe in this case, you have to consider the test suite and how you extract the test case. I think it's in this way.
Okay. So thank you once again. And now I think it's time for last presentation of the session.
It's not really that easy to test them manually. So one possible solution to test, to help in the automation of concurrent systems, is use model-based testing, or MBT, which the name suggests, as the name suggests, it's use models to represent the behavior of the systems. So there are still a few limitations when it comes to testing concurrent systems or applying MBT. The first one is that MBT requires as input a formal model, and model relies on precise mathematical notations, which is not really so common to use. We often use more casual notations like UML. So because of this restriction, it's a little bit difficult to adopt MBT. And when it comes to the concurrent behavior, it's not that simple to establish the relationship between inputs and outputs, because for non-concurrent systems, we often have, like, for each input, there is a specific output related to that input. But for concurrent systems, this is not really the truth. So because the interactions between the execution flows, we might possibly have like multiple inputs or multiple outputs. So it's not really that easy to predict the outcome of these interactions. And when it comes to outputs, especially in concurrent behavior, in concurrency, we have this behavior that we call quiescence or quiescence, that it refers to the absence of outputs. So having no outputs can mean different things. It depends on the context. So sometimes it means that there is a bug. Sometimes it means that this is an expected output, having no output. So we have to be aware of those conditions and need to develop solutions on how to deal with those cases. And finally, it's not really simple to describe some concurrent behaviors like race conditions or synchronization using natural language models. So to tackle those limitations, we are proposing a sound test case generation approach applied to mobile device applications. We are also integrating the solution with a dependency analysis tool to make sure that the generated test cases follow a logical sequence of steps. To deal with the key essence behavior, we are proposing a new conformance relation called CSPIOQ, and we are also optimizing the test generation strategy to make it more efficient. So, and finally, we are also providing some evaluation to verify if the generated test cases are more efficient compared to the ones that were created by our industrial partner, Motorola. So I'm going to show you guys how this works. So to generate the test cases, well, actually, I'm going to show you the contributions first. So to tackle the key essence behavior, we are introducing the new conformance relation called CSPIOQ, and we are also integrating the solution with the dependency analysis tool to make sure that the steps follow a logical sequence. Then we are proposing an optimization to the test generation approach to make it more efficient. Okay, so I'm gonna begin first by explaining the top most of this figure, the original generation approach, which is a bit more complex and a bit more formal than the other one. And later, I'm gonna show you guys how we optimized this path here below. So to generate the test cases, we use a tool called Target, and Target requires as input a use case model. But because we didn't have access to these use case models, we had to create a solution to derive use case models from already existing test cases. And to do so, we used a reverse engineering approach. So we basically provide as input a test case, and we have as output the use cases that we need as input for the generation process. So once we have the inputs, the tool Target will translate those use cases into a formal model, generate the test cases, and then translate it back into a natural language model. So we have as input the use cases, as an output we will have the test case or the test suite. So as I said, we integrated the solution with a dependency analysis tool to make sure that the steps would follow a logical sequence order. So to do that, we used a tool called Kaki, and Kaki uses two inputs. The first one are the test cases, and then we have the second input that is a dependency, it is a document where you're gonna describe the relationship between the steps. So for example, if we have an action, which is the step, scan radio station, and we have to say to scan radio stations, we first need to launch the FM radio. So we have to establish those relationships between the actions to make sure that we're gonna follow a precise logical of steps. So after we describe those relationships, then the tool will suggest a consistent combination of the steps, so we can make sure that the steps follow a logical sequence. As I said, Target translates a use case model into a formal model, and to do so, it uses the CSP model. I'm going to show you guys how we convert a natural language model. This is a step, writing natural language, into a formal model, formal specification using CSP. So in CSP, we have what we call a process, and the process communicates events. So in this example, in the first line, we have the process F1, and F1 is communicating those events that are related to the user action, system state, and system response of this step. And finally, in the line 6, we have a skip process, which means that this specification terminates at this point, or it means that this test case, this test step terminates at this point successfully. So to obtain the test scenarios from the CSP model, we use a tool called FDR. So this expression is actually a refinement, and it means that Q refines P if the traces of Q are a subset of the traces of P. So if this refinement is not satisfied, if it's not hold, then the tool will give us a counterexample trace, and this counterexample trace is our test scenario. Okay, so here we have this event in Q that is not in P. So because this relation is not satisfied, the tool gave us this counterexample trace, which is our test scenario. So this is a sound test case generation approach. So we say that the test cases are sound because they follow some properties, and those properties are created based on the definition of a conformance relation. So we are proposing a new conformance relation called CSPIOQ, and CSPIOQ is based on CSPIO. But CSPIO has some limitations when it comes to testing the behavior. The first limitation is that CSPIO does not cover the quiescent behavior, and as I said before, this is a very common behavior to happen on concurrent systems, so we have to somehow deal with it. And second, CSPIO have a property called output enabledness, which means that these steps are atomic. So for each input, there is a specific output. And as I said before, this is not true for concurrent systems. We may have multiple inputs or multiple outputs. So our objective is to relax those restrictions of CSPIO to be able to deal with the quiescent behavior and also to be able to cover situations where we can have multiple inputs or multiple outputs. So the first thing we have to do when defining a conformance relation is to establish the properties of this conformance. The first property of our conformance relation CSPIOQ is called input enabledness, and it basically says that the implementation is always ready to accept an input from the alphabet. So as you can see in this example, there are some loops, which means that the implementation is always open, is always ready to receive an input. So since we are dealing with the quiescent behavior, we need to somehow be able to recognize when this behavior happens. So to do that, we use this function called prioritize. This is an FTR function. And this function defines priority between events. So if there's no output event, then we're going to annotate the trace with this event that represents quiescence. But if there's an output event, then this output event takes priority over the quiescence, so quiescence does not happen. Okay. In this example, we have an input, so there's no output. That's why we annotated with quiescence. We have another input, we do the same thing, we annotated with quiescence, and we finally have an output event. And because it's an output event, it takes priority over the quiescent behavior, so we do not annotate quiescence. So we finally get to the formal definition of CSPIOQ, and it basically says that the output events in the implementation are a subset of the output events accepted by the specification. Here we have an example of that. We have this specification, and we have two candidate implementations. So in this specification, we do input 1, input 2, and then output 1. Those are the accepted events by the specification. And in this first implementation, we also have the same behavior. We have input 1, input 2, and then output 1. So we say that this implementation is valid for this specification, or this implementation conforms to this specification based on the definition of CSPIOQ. In this other case, we have input 1, input 2, and then output 2. So because we have an event output 2 that is not expected in the specification, we say that this implementation does not conform to the specification. So based on the definition of CSPIOQ. Now I'm going to show how we represent a test case using our formal model. So a test case is composed of a process that represents the test case, the input events, the union of the output events with the verdicts, And if the system behaves as expected, we have a pass verdict. If otherwise, we have a fail verdict. And if the system behaves in a certain, we have an inconclusive verdict. So to verify the execution of a test case against an implementation, considering the quiescent behavior, we use this process. And this process represents parallel implementation, the process that represents the test case, and those processes are running at the same time. And as a result of its execution, we have the communication of a verdict event. So in that refinement below, we will check for the presence of a verdict event in the traces of the model. And if this refinement holds, if it's valid, then we finally get to know which is the result of the execution, if it passes, if it fails, or if it's inconclusive. We finally get the definition of what it is a sound test case. So we say that a test case is sound because it does not produce a false failure, or a test case does not fail if you run this test case with a valid implementation. But if you run the same test case with another implementation and it fails, then we can say for sure that this implementation is not in conformance with a specification based on the definition of CSPAOQ. So now I'm going to show you the optimized version of the generation process. Remember that before we had to create a solution to derive the use cases from already existing test cases, so we don't have to do that anymore. Instead, we use the concept of atoms. So we extract atoms from the test cases, and then we permutate those atoms to create new test cases with the combination of those atoms. This is an example of how this works. Here we have a test case step, and in this test case step we have some actions. So an atom is actually the representation of an action. So here, add, edit, and remove are our candidate atoms, and what we do is to permutate those actions or permutate those atoms to create new test cases. So for each of one of these combinations, we have a new test case. So because our other generation path is sound, we also want to make sure that this new optimized version is also sound. But it actually doesn't matter if you follow the top one or the bottom one. If the result is also the same, you have in the final a sound test case. This is what we are saying, this proposition 1. But we actually don't have proof of this association yet, so this is a work in progress. We finally get to the evaluation. With this evaluation, we wanted to verify if the generated test cases are more efficient than the ones that are created by Motorola test teams. So to do that, we use two metrics, code coverage and bug detection. For the first metric, we applied a test mutation technique. So to do that, we follow these steps. First, we had to select an application and select some mutation operators. The mutation operators are the modifications that we're going to insert into the code. So next, we open the application to insert those mutations, generate the mutations using a mutation tool, and then to be able to execute this application again on Android, we have to sign the application, and finally, we did the mutation analysis. So as a result, the test case generated by Motorola were able to kill one of the mutants inserted into the code, and the test cases generated by the proposed approach were able not only to find the same mutant, but also another one. And this happened because As I said before, let me show. The permutations suggested a path that the test cases from Motorola usually don't follow. So because we have this option of generated a combination of steps, we can follow different paths and be able to uncover new bugs. We have a more recent result relating to those metric bugs. Those are real bugs. There's not inserted bugs, so this is a better result. We applied some permutations to applications like camera, contacts, and wallpaper, and we were able to find 18 plus bugs, and one of which was actually officially reported by Motorola testers. So this is a good result. And related to the code coverage, we wanted to verify if the generated test cases were able to cover more of the application compared to the ones that are created by Motorola. And as a result, we have the generated test cases actually covered a lot more of the application when applied to components and classes. So this is actually an initial result. We are still working on defining a more precise metric for coverage, but we already have an indication that we can cover more of the application than the original test cases. So in conclusion, we propose an approach to generate some test case for concurrent features. We provided the soundness of the proposed approach. We also integrated the solution with a dependency analysis tool to ensure consistency. And to deal with acquiescent behavior, we created a new conformance relation, and we also optimized the test strategy to make it more efficient. And finally, we conduct an empirical evaluation to verify if the test cases are more efficient than the original ones. And as a result, we have an indication that we can cover more of the applications, and also we can detect more bugs than the original test cases. So thank you.
So do we have questions for Rafaela?
So close to the end, you are showing the results of the coverage.
Yes.
So do you have a notion, you said you're still working on this, but do you have a notion of, because the intersection is not that high, right?
Yes, yes.
The part of the code that you are covering via your automated approach, does it cover something that's less critical, more critical? Is there a sense of that?
Okay, we have no idea because I've used a solution that captures all the executed code for the test cases, but we actually don't know what is being covered. So that's why we are refining the solution. We want to make sure that we are collecting only the lines that are related to the test cases, because when you capture those execution, we capture everything. It doesn't matter if they are related or not to the code, to what we are testing. So we want to make it sure that it's more precise. Okay.
More questions? I have one, at least. So you mentioned that your testing strategy detected at least one non-equivalent mutant more than Motorola's testing,
Yes,
right?
yes.
But there were any mutants that were not detected at all, neither by your strategy and Motorola test case?
Yes, there were.
And let's just wait for that. So. Do you think that the ones that were not covered, do they give you some insight on how to even optimize your strategy to detect even more bugs?
Yes, it gives us. But we can actually, we kind of chose the mutation operators that were closely related to the test cases. So, I mean, it can help, but yes, my final answer is a yeah. I think it can help.
Any questions?
Thanks, Rafaela. Congrats for the work. Very interesting and uncovering bugs. Yeah.
Okay, thank
And
you.
just out of curiosity, because then you generate more tests because you generate more permutations, right?
Yes.
And I was wondering, some of these tests are manual, right? They have to manually execute it or automated
No,
tests?
we execute all automatic.
Automated?
Yes, because we
Oh,
have the
because I was
automatic
wondering
scripts.
as a guy that,
Yes.
okay, I execute this permutation, but now I'm going to execute this other
No,
permutation to for you, right? So, yeah,
Yes,
if it's
exactly.
automatic, it totally
It's all
makes sense.
automatic because our goal is to automate the whole process,
Mhm.
but it depends on if exists automatic scripts. If the test cases are already automatic, then we will generate automatic permutations.
Just for automatic.
Yes.
Nice.
Any other questions? So I have the last one. Is this your strategy running now in the operation of models?
No, not yet.
So what would be the challenges that you envisage?
Oh, there are a lot of challenges because the first, I guess, since we are dealing with the Motorola original code, we have to be able to, how can I say, represent in the best way the create test cases that represent in the best way the original ones. So we have a lot of challenges because we not always have like a one-to-one compatibility between the generated test cases and the original ones. So it's hard to define a traceability between those, especially when it comes to the automatic environment. So we have some limitations in that case, but we are still working on that, finding a solution for that.
Okay, so I think it's time to thank Rafael again. And lunchtime, right, Neil?
Okay, good afternoon, everybody. Oh, yeah. So it's great to be back, physical, this time in person. So in the previous, before the pandemic, we always had these panels with very interesting discussions. And during the pandemic with the virtual editions, actually we didn't have opportunities to have panels. So it's good to be back and also have a panel and to discuss a relevant topic at the time. And of course, it had to be related to AI, right? AI and formal methods. And luckily, we have very qualified people here with us this edition. And I hope we have some very interesting discussions. I'm going to present myself. I'm going to be the chair, so I'll try not to compromise myself with any opinion about the topic. I hope you have a lot of arguments and don't agree with each other. So a fun panel is supposed to be like that, right? We also have Arthur online. He'll join us in a few moments. Yeah, and the topic is how is artificial intelligence? Can you go back? How is artificial intelligence influencing formal methods, challenges, and opportunities? So I'm Lucas Lima. I should have presented myself first. And I'm an assistant professor at UFRPE, the university at the Northeast in Recife. I'm also the current coordinator of the Special Committee on Formal Methods of the Brazilian Computer Society. And today I'll be chairing this panel with you with the help of these important guys here, okay? Just quick. I did some research. Of course, we've been hearing about AI for some time, and when all this fuss with AI started, I remember some colleagues of the formal methods community being quite, with a lot of criticism. Oh, we shouldn't rely on that. We can't trust those kinds of techniques, and people are trying to kind of create barriers. But then, yeah, we started seeing papers coming relating formal methods and AI. And now, a couple of years ago, we have even some reviews on formal methods, most, of course, to machine learning, how formal methods are applicable to machine learning and artificial intelligence. This one from Kim Larsen, how formal methods meet machine learning. Yeah, we have seminars about that. We have companies also investing and researching on the topic. And we also have even a GitHub with a catalog of things being done related to formal methods and machine learning. Lots of things emerging. And as I'm not an expert in AI, of course, I know a little bit about AI, so but when you're not an expert, what do? You ask an expert, right? So I did that. So I asked ChatGPT, how is artificial intelligence influencing formal methods? And according to ChatGPT, yeah, we have several topics, really interesting topics. Automated verification, AI techniques can automate the verification of complex systems, ensuring correctness, blah, blah, blah. Model checking, synthesis, formal specification and reasoning, natural language processing. Some people had some discussions about that here in SBMF. AI for bug detection and correction, static analysis, things that we know in the formal methods community. Hybrid systems, safety and security, of course. But although the title mentions how is artificial intelligence influencing formal methods, I thought it would be interesting to ask how formal methods are being used to increase artificial intelligence trustworthiness. And then, oops, we have formal specifications, formal verification, a lot of things that we've already known. And of course, if you have been using ChatGPT lately, there is a footnote there on the page. ChatGPT can make mistakes, so consider checking important information. So I think we can start checking some of the things mentioned there with these guys, know what they think about that. And yeah, I hope you all can learn from their point of views, okay? So the panelists, so we have Stefan Legrand from SRI. Stefan gave us a really interesting talk on SMT solvers yesterday. Eduardo also gave some nice talks on the Afrit's workshop, right? And talking about verification of AI systems. So we also have Professor Artur there in, yeah, he will be virtually with us soon. And also we have Thierry from ClearC. So interesting that we have a combination of academia, research, industry. So I'm looking forward to these discussions, these opinions, and their point of views. Okay, so we're going to start with Eduardo. Okay, and yeah, without further ado, the floor is yours, Eduardo. Oops, by the way, you should use that.
Hopefully the audio setup will do. I guess I mean, I prepared a few slides for this, but it's not real slides. It's just to get the discussion. So it seems to me that they want the panel to be a bit of a fight, so I'll try to make my opinions as strong and crazy as possible. And my first opinion is that I'm very confused about the title. For this reason, which is the next slide, which is not appearing. So I'll start talking about it. So okay, yeah, there we go. So what is artificial intelligence is not clear, but there's many methods that could fall under the umbrella of artificial intelligence. So artificial intelligence, maybe it's the imitation of human intelligence in some ways. So of course, any form of reasoning, any form of behavior that's a bit more complex than just doing addition and subtraction could be artificial intelligence. Especially in the past, most of artificial intelligence was symbolic. And so you have been doing artificial intelligence all your life. Maybe you haven't called it that way. So the title of this panel is how artificial intelligence has influencing artificial intelligence. Right? So nonsense. So what we are actually talking probably is the right side. So the machine learning and deep learning. So instead of being symbolic AI is the distributional approach coming from statistics. And that's a more interesting topic. So from now on, I will, like in my talk on Tuesday, I will assume that artificial intelligence actually means neural networks, which is in the light blue thing. But that's a controversial opinion in machine learning circles, artificial intelligence. Okay, so yeah, absolutely. So now we have another problem, which is that sometimes we get confused when we say formal methods and artificial intelligence. Is this artificial intelligence to improve formal methods or formal methods to improve artificial intelligence? So now I have a few slides on both. So the first point is that if you just want to improve formal methods, then machine learning is just a good heuristic. And people have been using heuristic all the time in formal methods. You know, choosing proof strategies, optimize. Sometimes you have parameters that you're optimizing. So, you know, maybe machine learning is just a better version of that. But there's lots of negative results that you take a standard technique in formal methods, you apply machine learning, it works less well, right? And then I think the reason why nowadays people are doing so much panels and workshops about AI and formal methods is because hype, right? It's the large language models have exploded, especially in 2023. And finally, there is attention from business. Finally, there's attention from granting agencies that want to throw money at you as long as you put LLM in your grant application. But large language models are, well, especially the ones like generative AI, they are random number generators. So again, maybe it's just a heuristic. It's not something magic that has conscience or whatever the machine learning people are selling you. And so the strong opinion that I have, and it's not just my opinion, it's shared by other people that work in AI safety, is that nowadays there's a lot of marketing behind a lot of machine learning products, especially large language models. So there are companies that finally have something that they want to sell, and they want to sell it to the largest number of customers possible. And so they are fighting against each other for control of this market. And so as a researchers, personally, I am sometimes confused about the capability of these large language models and the future of these large language models, because OpenAI is misleading me, and Google is misleading me, and Microsoft is misleading me, and big professors in machine learning are misleading me. They go on the newspaper and they make some claim about the singularity, about the robots taking over the world, about the fact that we need to do regulations, and these are not truthful statements from an academic perspective. There are ways to manipulate the market in such a way that they will sell more. And so there is a bit of a problem of sort of keeping a balance, like a balanced view, because there's this game being played above our heads. Controversial opinion, you can fight me. Okay, so let's talk about the opposite, which is the thing I've been working on, so it's a more informed opinion, which is how formal methods can help machine learning. And this is something that ChatGPT actually replied quite well. So one of the problems, especially in traditional machine learning, is requirements, because if you do image classification or text summarization, these are unspecified goals. And so in machine learning research, there's already a lot of discussion about what is a correct benchmark, what is a correct metric. It's difficult just to measure progress, let alone ensure safety, because you don't know what safety means. Again, think about summarization. What is a good summary? How do you measure the summary is good? This was the old problem for people doing summarization. But now, on top of that, you have, I don't want just my summary to be good. I want it to be safe. What it means, I don't know. So just coming up with a requirement is big result. And then, of course, since a lot of you guys are formal language people, maybe these requirements need to specify it in some actual formalized language that can then be processed by tools. And I see research just on that. So they assume the requirement is given, and they think about what is the most expressive language that can represent all sorts of requirements. And once you have that, then you have the problem how to check, right? And the big problem with neural networks is that they are big, and they are highly nonlinear, and they are, in general, very annoying. And if you want to be scalable, you can't, and not only you can't, but you have the problem that in machine learning, what the data scientists are trying to do is having the largest possible neural network, and from the verification side or the checking side, you would like to have the smallest possible neural network. And this is going to get worse, right? We have hardware accelerators, like the industry is going towards bigger and bigger neural networks, trying to have your phone run ChatGPT natively or something like that. So it will have bigger and bigger models, and it'll become more and more a problem to try and verify them. So the current verification algorithms are not very scalable. So if you come up with a better scalable verification algorithm, you get publications, or maybe you get rich, I don't know. If not, then you do testing. And this is, again, this is something that the whole machine learning field is built on, but they do testing like in an amateurish way, right? Testing in machine learning does not have a concept of coverage, doesn't have a lot of the more structured ways that you guys have to say, I have tested enough. And this is something missing, people working on, but we are still very beginning. So final opinion is that many, many times being in this field, I feel like this. So we have AI, we want to deploy it, the business is shouting at us, I want to use this, give me safety guarantees, but there's no way, there's no way even to make sense of what safety means. But this is perfect for us. This is jobs, this is grants, this is money. So we should rejoice and join the crowd of AI safety. And that's my talk.
Thank you, Eduardo. And now I think, next one is Stefan. Oh.
Okay. So by and large, I'm not claiming that I'm an expert in that question, at least not as much as Eduardo and others. But coming from SRI International, we do have some activities at the interface between what we should call symbolic AI or formal methods and statistical AI, machine learning and neural nets in particular. So how is one influencing the other? I mean, it's undeniable that there's been a revolution on the statistical AI side very recently, especially with those large language models. And one of the first consequences for us former Methodists is that, as you said, now if you want to get any funding, you need to say that you're going to involve some kind of LLM at some point. But that's fine because I mean there are plenty of things to do, plenty of topics to explore with LLMs. But it's quite funny that now if you want to get funded, you need you need that. So there's one way in which the field of formal methods could kind of fear a little bit the statistical AI thing. Like, I mean, statistical AI is stealing a lot of jobs. Like, there are lots of jobs that are now going to be done by statistical AI, and I think everybody's asking the question, where is my job going to be threatened by statistical AI? Are formal methods going to be threatened by it? And to some extent, I'm quite optimistic there. Precisely because, okay, what would the field of computer science or software engineering look like if formal methods didn't exist? It would be, you know, an art or a bunch of systems and software that, you know, sometimes it works, sometimes it doesn't work. You know, most of the time it works, but sometimes it doesn't. Who cares, you know? And if you're happy with that, then you're probably happy with LLMs taking over the world, because that's pretty much what you get, right? Sometimes it works, sometimes it doesn't work. So, to a large extent, I could argue, this is an opinion, that like formal methods start exactly where machine learning stops, right? So it's whatever machine learning cannot do provides guarantees, you know, beyond some kind of statistical guarantee, is precisely what formal methods are designed for. So in that respect, almost by construction, they're really a complement. Okay, but I'm still going to point out a few things that we should probably think about in terms of positioning as formal methods people. And one has to do with marketing. I mean, it's clear that there's so much money going into statistical AI that, you know, discrete mathematics, formal methods people, you know, we also have to make our voice heard a little bit, so that we're not drowned in all that noise that we see. Like, you know, if I look at my LinkedIn feed, it's like blogs and blogs and blogs about LLMs and things like that. So in particular, like about 6 months ago, there was an article that came out that was called Deductive Verification of Chain of Thought Reasoning. And I saw deductive verification and thought, oh, that's interesting. I know what that is. You know, we've been doing deductive verification for years, so I'm thinking of, you know, weakest precondition calculus and you know, things like that. And I started reading the abstract, and part of it is, hold on. Inspired by how humans engage in careful and meticulous deductive logical reasoning processes to solve tasks, we seek to enable language models to perform explicit and rigorous deductive reasoning, and also ensure the trustworthiness of their reasoning process through self-verification. And that sounds very formal methody. Yeah. So I was very excited. I read the article. And by the time I reached the end of the article, I realized, you know, those authors have never heard of formal methods. The vocabulary is extremely close, but there was, I mean, it was clear that they weren't aware that there was such a field of formal methods. I'm not saying that what they did was useless, on the contrary, but it's quite strange that people with no background in that, in this article, they came up with what we call a notion of Hilbert-style proof system. Okay, that's something that was invented more than 100 years ago. They came up with the notion of unsat core. So when you have something that you prove, you want to minimize maybe the hypothesis that you need to prove it. And they came up with these ideas completely independently. So that was kind of cool. A little bit separated from what we do, because we work on formal abstract, abstract syntax trees and stuff, and they work on natural language. But it's a lift to natural language of those concepts that we have in formal methods. But the most interesting part there was that the notion of deductive verification was as follows. Like, you ask an LLM to produce a chain of thought, so a reasoning process from premises to conclusion, and you ask it to, you know, split that reasoning into small steps, and then they have what they call a verification process that's going to inspect every little step and you know, validate is it valid or not valid. But the funny part was that the way that they do this verification was not to invoke like a proof checker or one of our tools. It was to call another neural network on that particular step and say hey or nay about whether that sounds correct or not. So it's quite funny and interesting. So I think there's a lot of communication to be had between the communities to actually realize that we have some of the same concerns, but we have different technologies, and in many cases they can kind of concretely marry each other. But there's a little, I wouldn't say a threat, but something that we need to think about in terms of vocabulary for the, for people who are not computer scientists and when they hear deductive verification and rigorous validation of proof steps, etc., in this article or in our articles, to them it presumably sounds like the same thing. I mean, to me, it almost sounded like the same thing until I read the article. So there's the question of part of the statistical AI kind of starting to reuse vocabulary that we use. And at some point, the question comes of, well, for most people, is that kind of verification, validation, or what you call it, good enough that you actually don't need formal methods in our sense? So here we have to be careful and really explain, do some pedagogy about, in what way is what we're doing different from the kind of validation that's, because like if you type deductive verification in Google right now, that article is the second link already. So, so we have to think about that. And to be honest, we also have to think of the notion of trust, the trust base. Like, if I were the devil's advocate and I look at this article and there's some kind of black box that says A or nay on each reasoning step, so there's that technology, there's kind of our technology, maybe or a proof checker that we've written, maybe for Alithi proof format, there's a proof checker and it's going to check every step. And to the user, it's also a black box that says A or nay, right? So is there a difference in nature in the black boxes that validate these things, in our black boxes and in machine learning black boxes? Is there a real difference? Hey, to be honest, our own software could be buggy. It could say the wrong answer. An SMT solver, to most users, even in formal methods, an SMT solver is just a black box that says A or nay, and we have bugs in our SMT solvers, so sometimes they work, sometimes they don't work. In some hopefully rare cases, they give the wrong answer. Maybe to most people, this just sounds like what the neural net does. So what more guarantee do we bring? I'm being the devil's advocate here, like deliberately. All right, so that being said, so we have to be careful about the vocabulary and trying to identify what do we bring on the table, like what's the difference in essence about some black boxes giving some answers. Okay, and it's also, the new situation is also a lot of plenty of opportunities for us. Like you mentioned, our formal methods tools are full of heuristics. Like every procedure that we write in the field of formal methods is actually not a deterministic algorithm. There are plenty of points where you have to choose something, choose a variable, choose a truth value, choose a value, choose, And our tools, our implemented tools have plenty of heuristics. They're not that great, actually. I mean, we come up with some stuff like activity-based scores for SAT solvers and stuff. It's very likely that statistical AI can actually give us a boost or give us much better ways of dealing with the non-determinism of our algorithms. I mean, SMT solving is just trying to find an answer in a big search space. You are going to traverse the space in some way, and leveraging AI, machine learning to resolve the non-determinism of that traversal is I think very, it's an opportunity for us. Now that being said, in those tools, we usually need those heuristics to be very fast. So probably if you are going to, you can't probably involve a huge neural net that's going to take some time to execute in order to know what's the next variable that you should decide. So when you want to use AI within, say, a solver, usually you want very cheap ways, very fast ways of resolving the non-determinism. So that's one of the aspects that we look at SRI International, is how to use AI or machine learning to inform the heuristics of formal methods tools. And we do that, we try to do that in the automated reasoning part, but also in the proof assistant interactive theory part. We've got a proof assistant called PVS. And proof assistants are hard tools to use, so we use machine learning in order to give suggestions to the user about what's the next tactic that could be useful at that point. So we do some research on that. On automated reasoning, typically one of the heuristics that we need is a variable ordering. In which order are you going to take the variables? And there again, we are using some machine learning to try and predict what's the best variable ordering for solving my problem. Now I'm just going to finish with one activity that excites me quite a lot at SRI. We're just starting it. You were talking about the two directions, how formal methods can be applied to machine learning, and how machine learning can be applied to formal methods. There's one area in which you can see it from both angles, which is synthesis. Right, so in one direction you can see, those LLMs are able to spit out some code, right? And because it's been spat by some machine learning model, you don't know exactly if it does what you want it to do, and you would think, well, formal methods are great, they're exactly there for that. They take the code, they can verify it. So one way of seeing the problem is really bringing some guarantees about the output of LLMs when they produce code. But another way of seeing it is that, well, synthesis is something that existed way before LLMs, right? In formal methods, we have code synthesis, program synthesis techniques. Like one class of such techniques is called SYGUS, syntax-guided synthesis, in which we basically give the syntax, the grammar of the kind of trees that you want to see come out of the synthesis, and then you've got some techniques to verify that what you spit out satisfies some formal requirements. And before LLM existed, the ways in which you would try out some of these ASTs is either by enumeration or by some symbolic techniques that are not super smart. So you could think, well, let's take a SYGUS system, but in order to generate putative programs, putative pieces of code, instead of using some enumeration or something like that, just use an LLM. So that's also seeing a traditional formal method thing and trying to boost it with LLM. So this is the same problem, just expressed in two different ways. So I think that's quite a nice area. And I think, was it Luca who was talking about using ESBMC in order to verify the output of LLMs? So a couple of groups are trying that. We're trying that as well. We are using an LLM to, like one of the experiments that we did was to have an LLM spit out some planning solutions, and then using an SMT solver to check that the code that's spat out is satisfies the planning constraints. But we want to move to more sophisticated examples, and I'm going to finish that. One thing that we want to do here is maybe not wait until the LLM has produced the full answer before you start applying formal methods to it, but try to apply those formal methods more like on the fly. Because once you have a big snippet of code, it may not be trivial to actually verify it, but you could start verifying the output of the LLM token after token on the fly. For instance, you could check things like it's well typed on the fly, And you can actually enrich a typing system with really rich specifications and keep doing that typing on the fly of the tokens that the LLM outputs. In fact, most LLMs actually don't output a single sequence of tokens. They do some kind of something called beam search. So there are several options. And you could use formal methods to actually filter out some of the options that actually don't work for typing reasons or for verification reasons. So by doing that, we hope to get a tighter loop, a tighter feedback from formal methods in order to validate the output of LLM. So that's one of the projects that we're working on. And I'm going to stop here.
Thank you. And,
yep.
But by the way, just a quick question about this paper. Don't they at least cite in?
No.
Really?
No.
Wow.
No. But I think they don't know about it.
Yeah, yeah, but at least the reviewers should warn them.
So it's true that if they had typed deductive verification in Google at the point when they submitted the articles, they would have found hundreds of links to formal methods. Maybe they didn't. I don't know.
Yeah. Okay.
All right.
Thank you. And now we're going to have some industry perspective.
Serious.
From Thierry.
I'm going on this side. Okay, so I started my career in the beginning of the 90s in a French company called Neurosystem, using neural networks and signal processing for detecting aggressions in the Parisian metro, detecting Russian nuclear submarines in the Mediterranean Sea, or detecting also helicopters. So helicopters, you hear them, so military helicopters, you hear them before you see them, and when you see them, they have already fired. So you need to know if it's friend or foe. So, and the first Gulf War started in Iraq, and we just stopped everything, back to serious business, and I moved to ClearC to work on theorem prover for the BMF. So, and now, since 2 years, I'm back to business, so mixing both of the worlds, so this is what I'm going to share with you. I would like to focus, because your guys, your presentation were a bit large, just to go for concrete applications on ground transportation and autonomous mobility. So I would like to start with the definition of safety, because I remember the safety properties you define for your neural network were a convergence for the correct weights. Completely different definition, of course, because the picture is larger. So when you deal with safety in the real world, you deal with failing software-based systems, meaning that your system is able to fail. And usually, so in this community, so this is a usual development process, we just work on the mistake we can make at the specification level, and we are very happy when we can demonstrate that something is incorrect. The problem is we have many more ways of failing. So you can still have a good specification, but you write the wrong program. So again, the B method or Formais, you have a number of means to verify that the program you get is the correct one. You can have the correct specification, the correct program, but your compiler is buggy, and the binary you get is not exactly the one that you are expecting. How many people in the room are having a look at their binary? Yeah, okay. The only one I know are cyber hackers, people working in cybersecurity, because they want to be sure that it's not doing something unexpected. And then you still can have a good binary, but you have a wrong execution. So the first thing are failures that are systematic, meaning every time you do it, you can't avoid it. The wrong execution means that the processor is not a perfect execution machine, so it can be perturbed. For example, in the train, you have the power lines that can emit electromagnetic waves, or you go into the space and you have the high energy particles. So usually we have to use redundancy So you multiply the number of compilers, you multiply the number of processors on which you execute your program, and you have a voter. You can have a bad hardware, so you think that the processor you are using is the correct one. Sometimes you buy a processor, but inside you have sockets that are not connected, or even worse, there is a gray market in China. So when you test your chip, some chips are not going through the test. So they are going to the bin, trash bin, and there are some guys who capture and they put it again onto the market. So you can have something that is not exactly the same, the thing that you are looking for. And the last one is you have the entropy law, meaning that you can, even if the processor is the correct one, you are going to lose some gates. So for example, you expect that when you compute 2 plus 2, you get 4, but sometimes you're going to get 5. Or you can have a drifting clock. So when you program an interruption, you say wait for 1 second, maybe you're going to wait for 2 seconds. So we need some to have a redundant clock as well. But it's not finished. So we can also have a wrong specification for the environment, because it's, I remember being involved into the review of a software. So it was developed in B, 100% proven, but the specification considered a shorter platform, and we triggered emergency braking all the time because the train entered the platform too quickly. And you also have an exploitation procedure, so this is where the human people are entering the loop. A system is not safe by itself, so you need to set it, to verify it, and to put it into exploitation. So many ways of making mistakes. Some parts can be processed with formal methods, others involve technology means. But it's more complicated than just ensuring that the memory is not corrupted. Okay. So when you go for safety critical system, you have standards. The standards define that, in fact, the safety is by design. You can't do a functional development and say, now I'm going to add something to be safe. In fact, it's just at the beginning that you need to define the redundancy and so on. And then when you have a look at the standard, so this is the industrial standard used for most applications. And here you have a collection of techniques, so you can't read it, it's not important. And you have the safety level, 1, 2, 3, 4. So 1 and 2, you can use one processor. Still 3, still 4, you can kill people, one people, several people. And so here you need redundancy, so you need several processors. And you can have a look at, here it's written formal, semi-formal methods and formal methods. They are highly recommended for SIL4. But if you look just above, artificial intelligence, and you can read not recommended. So this is the current version of the standard. So not recommended means it's not accepted, because you have to convince someone that it's applicable. And the main reason is a lack of explainability. So to get a certificate, because in most industries you need to get this certificate, so most industries, except automotive industries, so you need to convince someone. It's not a mathematical certificate. And this person is directly responsible for future accidents if they happen. And so, so this third party is supposed to be independent. So you all know what happened with Boeing with the 737 MAX. There is something that is less technical. So it's a French company called PIP, producing breast implants for women. And the implants were certified by a German TÜV. So the TÜV is directly responsible for the certificate. And there were some problems with the implants. So they were paid €500,000 for the contract, for the certification. But because of the problem, they were obliged to pay 30 million euros. Yeah, so this is just to summarize the formal methods that we are using for safety application in my company. Just to sum up, so we are doing software development. So there is requirements, a human that writes some formal model and some C source code transformation, and then here we have means of verifying using theorem proofs. We verify data the same thing using a model checker. We can do system level proof using B and a theorem prover. Smart card certification, theorem prover with B, and also software verification. So everything is a well-oiled process accepted for certification. So you can see here a number of formal tools, formal languages, and most importantly, human everywhere. And this is really important to have a human in the loop. But most importantly, so we have seen that we can define a technical product that can go through certification. The main problem is most of the time, this part, the human factor, is not part of the specification. So this is in Sydney, in Australia. And have a look at the girl. She just puts her hair in the doors. And the problem is the door is closing and the train is going to leave. So it's going to stop, and there is no bad ending. No, of course. So the problem is you can't consider that human people are going to contribute to the safety of the system. So you create a system that is supposed to improve the safety, but in fact you are creating a new system with zero risk. And the problem for AI is you are supposed to be based on history, but you are creating a new system. So how to deal with this innovation? Some word about security. So in the railways, yeah, we are connected. So the two different new signaling system, ERTMS in Europe, that is using GSM for the main lines, for the high-speed trains, and the radio for metro with the CBTC. And of course, we've got the first attack last October in Denmark. All the drivers have a tablet on which they receive information about the presence of obstacles on the track or speed limits. And the IT operator was attacked. So the train drivers stopped to receive information and they were not entitled to go forward. So all the trains in Denmark were stopped during 6 hours. So no safety problem, but when you are passengers, you're not happy. And the problem is, yeah, you have, most of the time, you have state-level attackers with a lot of means, and all the equipment that are installed on the tracks or on board have been installed for decades. So autonomous mobility, well, it's just for the fun. So is artificial intelligence going to save us? So this is the view. So you have tons on YouTube. You have tons of videos about this thing. So this is the view, how the environment of the Tesla car is being perceived by the computer. And here you have a car with horses. So just have a look how it is analyzed. So there is a truck. There is a car, a truck on the opposite direction, a car with a pedestrian. It's not bad because they can see the legs of the horses. I mean, it's complicated. I'm quite sure that it was not part of the learning of the testing of the car. And the second video is this one. So the marketing thing was, we are not going to make any more human errors because of the automation, but now you have robot error. And so it was recently in Austin, you got a traffic jam of self-driving cars. But again, it's complicated. You have so many different possibilities for the environment. difficult to have something that is able to deal with all the situations. And so we have the beginning of work on the how to explain artificial intelligence. So this standard is being written down. So normally the standards are supposed to represent some history, some experience. Here we start from scratch. And the two guys in charge of the standard, one is the CIO of Waymo, so the car manufacturer, and the second one is the CIO of NVIDIA, the company providing hardware. So we don't know if this is going to be applicable, at least in Europe. Okay, so now how we are using AI at ClearC in my company. So 3 points. We are in a European project. So as you say, we can capture a lot of money for when you mention European, we mentioned artificial intelligence. We are working with UIC, that is the International Union of Railways, to see how we can certify new systems that are going to include machine learning, because train manufacturers are pushing in this direction. And we are also involved into a demonstration project where for autonomous trains. So the first one, the project, as you mentioned, we are trying to use machine learning in different ways. So first thing, it's not for controlling the train, but for easing the proof. So three different aspects. So with Atelier, we have a number of provers that we can select. And when you are doing continuous integrations, you have hours and hours of proof. And if you select the correct prover, so we train machine learning things, and we are able to cut the proof time by 30%. We used also the same approach for trying to define a proof script, so demonstration using assembly language for the proof. At the moment, we are not very happy with the results. So Stefan, the proof obligations are here. So we have 500,000 proof obligations that are publicly available. The second thing that we tried is to use, so we have tons of existing models, so we have specification implementations, and the idea is to be able, like Copilot, when you write a specification, to generate or to provide some aids of how to write the implementation. And the last thing that we did that is very, very surprising is to be able to provide some assistance when you read some technical specification. And so we use a public document that is a specification of the ARTMS thing. So it's very dense. You have 300 pages, a lot of details. And we ask one question that required to understand everything, and he provided the perfect answer. So at the moment, we are very puzzled by this result. So the second thing is about UIC. So UIC, probably you know, this organization is supposed to ensure railways consistency worldwide, meaning that when you take a train in France, in Brazil, or in China, the safety level is supposed to be constant. So all the train manufacturers are part of this organization, and they write recommendations that can become technical specification and then standards. And this is part of the project, how to examine and evaluate existing methods, in particular the one that include artificial intelligence. And the question is how to help the certifiers. So again, the people that are directly responsible for the accidents to understand what's going on and how to demonstrate that the safety level is ensured. And so at the moment we are on the step 2, where we are going to write recommendation, and then we are going to experiment with the UIC members. So up to the end of the next year. And then we have a contribution to the standards. And then the 3 projects where we involve for autonomous trains. So the autonomous trains, you replace the drivers by machine and with and cameras. The idea is to use lightweight regional trains where we have low traffic lines, and formal methods are just used for the safety activities we have to handle, that is communication and localization. And for everything that is based on AI, we just do not realize just a black box, and we develop safeguards to ensure that what has been detected is correct. So usually we have a voting, so we have different vision-based systems that provide an analysis of the situation, and we have a voting thing. And then we are also involved into, so it's not autonomous cars, it's autonomous shuttles. So for public transportation it's different, because in this case you can have a remote control, take into account that unexpected behavior. And what we are doing is we are ensuring the safety at very low level, and for the artificial intelligence thing, in fact, we need, this is the case in Europe, so in the US, I know that you can have vehicles on the road without anyone. In Europe, at the moment, you need to have someone to ensure the safety. And so the challenges are, at the moment, we can either use formal method for developing safeguards, or are we going to be explained AI? I don't know. We need engineers to be able to handle both AI and formal methods. And I see the prompt engineering just to assist, not to replace engineers. And for me, the main risk is now that we connect everything, we have all these risks, safety, security. How are we going to control the system for which we have no history? And it's difficult to handle the new unexpected risk.
And now we're going to have Arthur.
Hi everyone, can you hear me?
We can, just a second, so we're going to show you on the screen. Okay.
Hello, hello, can you hear me well? Hi Edward.
Can you speak so you can...
I can't quite hear what you're saying now, but I was listening before, so shall I just go ahead?
Yes, please.
Okay. Thanks very much, and I'm sorry I cannot be there in person. The plan was to be there, and I'm still hoping to visit in the near future, but that was not possible this time. It was very interesting to see the ChatGPT answer to the question of AI for formal methods and formal methods for AI. It's a lot more complete than what I sketched here. So I'll give you my kind of summary, perhaps, and then try to touch a bit on what was mentioned by the other panelists. In my line of work, when I think of AI for formal methods, I think of mostly verification. If you look at, for instance, what the team at DeepMind has been pushing forward, there is a common thread in many of the systems that they put out there to do with solving or approximating combinatorial problems. So trying to address combinatorial problems where you do have the ability to perform a lot of simulation. So this is what you see in AlphaGo and in AlphaFold, and more recently some of the other systems. And so I think of that as one main area where the research can develop and have a very strong practical impact. And so we are basically talking about neural networks as SAT solvers. So this is also some of the research that we are pushing with Azure. Neural networks as SAT solvers. I don't think we are there yet in terms of beating the best symbolic SAT solvers, but it's very interesting to see how this could progress, especially as we try to scale such systems to solve these difficult combinatorial problems. So that's my take on AI for formal methods. And on formal methods for AI, then in my perspective, we need to think about what we call neural symbolic systems. And explainable AI was already mentioned, but in general, in a neural symbolic system, you have a cycle where you hope to explain the neural network, but also if you have a system spec described in some logic, there are ways of constraining the behavior of the neural network with that. And these can be thought of as either hard constraints or soft constraints. So the spec is either a soft constraint, so training of the network can revise it, or in some more recent work, it is presented as a requirement, as a hard constraint to be satisfied by the network. And in terms of practical applications, we are seeing now this being used, for instance, with knowledge graphs constraining large language models. So this would be an example of that idea of a system spec that I think first came about in the context of neural nets in the area of neural symbolic AI. And there also, there is, and it was mentioned also, work on verification of neural networks. And this is an interesting but challenging area. And if we may find it hard to get some results on in that space, we could at least try to verify the outputs of the neural networks, right? So I'm thinking verifying, for example, the code that is generated by AutoGPT. So this is what I had to say about how neural symbolic AI connects with this community, I think. But listening to the other speakers, I also had I wrote some comments here, and I was thinking about this video that I don't know if you guys seen, this Gemini video that just announced by DeepMind, because there were references to AI hype, and I think yeah, if I may, can I share this video with? I don't know if you can see this.
You can share your screen.
I'll just. I don't think this is hype. This is Google DeepMind developing something that I thought was very impressive. Let's see what you guys make of it if you haven't seen it yet.
We're not seeing it here yet. Okay.
Here we go. Tell me what you see.
I see you placing a piece of paper on the table. I see a squiggly line.
What about now?
The contour lines are smooth and flowing, with no sharp angles or jagged edges. It looks like a bird to me.
What if I add this?
The bird is swimming in the water. It has a long neck and beak. It is a duck.
Yes.
A duck is a type of waterfowl in the family Anatidae. Ducks are closely related to geese and swans. The duck appears to be blue. This is not a common color for ducks. However, there are some breeds of blue ducks. These are typically not as common as other duck breeds. It is more common for ducks to be brown, black, or white.
Are you sure?
What the quack? I was just talking about a blue duck, and now you're holding one. It looks like blue ducks are more common than I thought.
Would this float?
I'm not sure what material it's made of, but it looks like it might be rubber or plastic.
What if I tell you it's making a squeaking sound?
Oh, if it's squeaking, it's definitely going to float.
Nice.
It is a rubber duck. It is made of a material that is less dense than water.
Can you teach me how to say this in a different language? And give me a few options. Ooh, can you explain how to pronounce the Mandarin one? Is it Yazi?
Yazi is pronounced with a first tone. In Mandarin, there are 4 tones, which are essential to distinguish the meaning of words. The first tone is a high, level tone.
Oh, okay.
The duck is in the middle of the ocean. There is no land nearby for the duck to rest or find food. It is unlikely to find ducks here naturally.
Okay, based on what you see, come up with a game idea. Oh, and use emojis, please.
How about this? We can play a game called Guess the Country.
Sure, let's do it.
Clue 1. This country is the home of the kangaroo, the koala, and the Great Barrier Reef.
Oh, that's easy.
Clue 2. This country loves football and has won the most men's World Cups in football history.
No.
You are trying to get me to find the paper ball under the cup. I accept the challenge. The cup to the left.
Nice.
I know what you're doing. You're playing rock, paper, scissors.
What do you see now?
The fingers are spread out to look like the wings of a butterfly.
What's this?
Big ear and barking mouth. A dog.
Sweet.
The coin should be under the right hand.
I don't know.
The coin is in the left hand, using a sleight of hand technique to make it appear as if the coin has disappeared. Both objects are round and flat.
There you go.
Both are food. The orange is a healthier choice than the cookie. Citrus can be calming, and so can the spin of the fidget toy. They are both examples of popular...
Okay, so you get the idea of what is going on there, and it's the multimodality built from bottom up, and they also created Gemini Nano, which I think will be quite impressive to work with mobile phones. And the online interaction going on and the recognition, which I find very, very impressive. I think we have to say there is some kind of reasoning happening, but I agree with the point that we want sound reasoning, not the kind of reasoning that may be happening there. And we need, as researchers, to define it and formalize these things properly. But it's impressive to see this kind of common sense reasoning take place from a system that was built bottom up. So yes, I think there is a lot of hype, and I think that there is a lot of garbage, but the garbage will be filtered out. And I also think that this is highly impressive and that there are many opportunities there when it comes to use and applications. Of course, there are risks as well. We can talk about that. Now, just to mention in terms of the scale of these systems, right, and the difficulties associated with trying to verify properties of these systems. I would argue that scale is not all that you need. There is, in fact, a strong engineering drive by very few companies that can do this type of engineering effort, which is impressive. But we are also seeing some smaller systems achieving good performance. And when we talk about this neurosymbolic cycle, where we try to extract descriptions which are symbolic from these neural networks, frequently what we see is that as we close the cycle, we can build more compact systems. So there is a lot of stuff in there that's actually not needed, and so I think there is hope. One, to build such neural network models that are more modular, so that we can control how the scale is derived from these systems, but also to close this loop and then perhaps derive more compact systems with same level of performance. Just to wrap up, I want to have a chance for a bit of debate. The example of the self-driving cars, that industry is struggling right now, and it's a very good example that we can take into account. And again, I think there is this difficulty to handle exceptions, right? So the example there was an exception, and by definition, machine learning systems, they try to generalize, and so the exceptions are not handled well. And so again, these logical constraints or specifications can be seen as exceptions that need to be encoded into these systems. So I'll stop here. Another example, if we have time later, a recent paper that just came out that I think is it's not very relevant in practice, but it's very interesting for the research community. It's the question of arithmetics, right? And how such large language models may deal with, for instance, multiplication, and how they handle multiplication. So we see that in this recent paper, they can do multiplication very well, but there are some tricks. And then after a certain number of digits, it starts to fail. And we need to make sense of that. We need to understand why is it like that. If the system had learned a proper algorithm, a method, and then it wouldn't fail after a certain number of digits, right? It would either know how to do multiplication or not. So I'll stop here because I'm conscious of the time, and it's probably better if we have a bit of a conversation. Thank you. I don't think I can hear you. I think I lost your sound, so maybe when it's shifted to mine, should I maybe leave and come back? Yeah, I can hear you now.
Okay. Now, hear me? Okay. All right. Can we try now? Okay. All right. I'll start. So thank you very much. It was all very, very interesting. And I feel better. I now am sure that we are better than they are. But I agree. I think that when you need assurances, there are way too many things that AI doesn't do, right? But what I was wondering about something that Arthur said, that we can use AI as a set solver, and that would be kind of an easy example to check. I mean, if you have an answer, you can check if it's true or not, right? And that would worry me, or I don't know, since I don't do AI, it would worry me that if this is going to work. I mean, I would like to know your opinion. If things like this are going to actually work better and better to the point that they might actually replace things like the equivalent set solvers. I don't think so, but I would like to know your opinion.
Okay. I think I just want to make one point, and then I will let people that know more about such solvers speak. Which is, I think the language we use sometimes confuses us. So I think when people say something like, "Yeah, let's replace such solver with AI," they don't mean replacing the core algorithm. They mean doing a such solver that exactly like the traditional ones, but all the parts that are based on heuristic choice, now they are boosted by statistics. So that's the same with the AlphaGo, right? It still uses technique it's still doing a tree search in the game space. It's just that now the choice of which states to prune and which states to explore more in depth are done via statistics instead of some simple heuristical rules, right? So
AI is just another piece of the puzzle that we have to try to put together.
yes, so like sometimes what I find it easy is every time I hear AI is, can I replace AI with very smart heuristics? Does the sentence still make sense? If yes, then that's what's happening. If not, then I ask more questions. But maybe someone has more qualified opinion.
Oh.
Double microphone.
I'm not sure it's more qualified, but I mean that's using AI to have better heuristics is a natural idea. I would almost say the lower hanging fruit. But at the end of the day, we have this CDCL algorithm for SAT solving. Nobody's proved that this is the best algorithm that exists for doing that. I mean, so far that's what works best. But maybe in presence of AI, statistical AI, maybe we should allow ourselves to think outside of the CDCL box, for instance, for SAT solving. So who knows? If you ask me, what other algorithms could we think about? I wouldn't be able to give you an answer. I don't know, but maybe that's still a possibility. What I've seen happen is using AI outside of CDCL in order to solve, and I'm putting this in quotes, SAT problems, but it's more like to predict the answer, to predict SAT or unsat. There's been a bunch of papers doing that. But if you just ask that, if you just ask for a prediction, SAT or unsat, are you just happy with that or not? If it's SAT and if the AI actually produces the Boolean model, then yes, you can check it. But I'm thinking about the unsat case, in which case, well, the AI predicted an unsat, well, that's going to be very hard to get any confirmation that this is the correct answer beyond actually redoing a proper search and having some kind of proof of unsatisfiability. Yeah.
It's like a closed and open world in the ontology, right? First, you cannot guarantee, and you have false, right? False or no.
Yeah, and from a safety point of view, I mean, whatever, if it's able to solve the problem, but in our case, as I explained, we always need to have two different machine learning things able to provide the same positive conclusion. One is not enough. So whatever it's a black box. So it provides an output. So we, in our case, we are using several SMT SAT solver provers. And if two different devices developed by independent teams with different technologies obtain the same result, we consider it's okay, whatever.
But, okay, so what if ChatGPT predicts that the answer is unsat and Llama 2 predicts the answer is unsat? Are you happy with that level of proof?
I don't know. I'm not the guy responsible. Who is going to take the responsibility to say yes? Maybe on one point it's not enough.
Can you guys hear me? Can I just?
Yes.
Thank you. Just to say that it's not just heuristics. So in neurosymbolic AI, we have been working on trying to add logic into neural networks, and I think it's important to make this distinction that was made earlier about AI, machine learning, and neural nets. We can represent propositional and propositional modal logic in neural nets and have some soundness guarantees. When we add learning on top of it, then it messes it up. And then there is the question of now what is being represented by these models. So if we just use the network for inference, then that's what we are doing with restricted Boltzmann machines and such solving. But we cannot beat the best symbolic systems, which are also more tailor-made for specific types of tasks. But it's interesting to wonder about the question of, what are these algorithms that are being produced? Now, when it comes to the explanation, what we call knowledge extraction, it's what I think we're going to see more and more is attempts to explain not the entire system, because as you know, these are now up to billions, if not trillions of parameters, but explaining elements and assuming that parts of it are okay to stay as black box. So if you think about a convolutional neural network, you may have a whole bunch of convolutional layers that you can assume are just doing the object recognition part and you're happy with that. But then there is a crucial layer where, before the first fully connected layer, where you need to make sense of what these kernels are doing. And so you can try to extract rules from these and reason about those rules. So I think this can open up a number of possibilities. But of course, if we just scale up without such considerations, then the challenge is huge.
Okay, anybody else want to share some opinion?
I want to do a question. I don't know if I get it correctly in my head, but it is correctly to say that formal methods, it's like rationalistical approach to solving computational problems, and AI is an empirical method, an empirical approach to solving computational problems. Is this correct? It is correct to say that? Thank you. Thank you.
I would agree with that terminology.
Yeah. Okay. Anybody else? Okay. Anybody else? Any
Just to go back to the point about what are because if we can achieve better performance from these highly distributed systems, then there are some algorithms and methods that are being called upon that we may not quite know what these are. Are they being invented? And yes, maybe they are being invented and hard to obtain because these are difficult to specify and a lot easier to learn. That's why with neural networks, so the prototypical benchmark is MNIST, handwritten digits, difficult to specify, easier to learn. But I think that there is still some specification, and we need to develop the research in that direction. So yes, but I think there is ultimately a combination of the two.
Okay. Anybody? Edja?
Okay. I'm not sure if this is a question or more trying to raise some doubts. Years ago, I read a paper from Pamela Zeif about what was soft engineer at that time. It was like 30 years ago, I guess, or over that. And she used the example of a car. A car, you get materials from different sources. Glass, rubber, steel, and you put them together at different components with different functionalities and parts, and guess what? It works. A car works, right? So my question is it not correct, but what do you guys think about AI and formal methods collaborate in an effective way? We would need to find at which points of the weakness and strong part of each other they should meet, just like a glass and a rubber meet in a car to make the windows protect as they should. And I remember the talk from yesterday, Stefan, about the example used, like spotting the parts of the search space, right? And it was curious because I thought exactly about that. Would that be an AI task? To spot the search space and say, hey, look at here, you have more chance to find some satisfiability in this space, and forget that. But in the end, which parts of AI informal methods should be glued together to make it work? Would that be a good road to follow, a path? That's my question. Thank you.
What I forecast and the thing that I just presented is modeling. So just, but I see it's just an assistance. So the engineer is always in charge of the whole thing, and is just going to receive some hints, some help for completing his task. So it could be modeling, because you're not the first one to model to address this this particular problem or sub-problem. And so you already have smart people who already provided the correct modeling, and the same thing for the proof. For me, it's the two different aspects for this thing. Modeling, proof, or testing, or whatever.
And just before, just to confirm what you just said, because I've been recently to Models, the conference in Sweden, and when they're talking about AI there as well, they also, most of the talks are related to that kind of support as well. It's how to provide, given the models that you have, and give some hints or how to start, and some efforts in early validation of those models as well. And yeah, I think other areas also think that's one way to go.
Yeah, so I think I agree with you, Edja, in that there's clearly an area where it's perfectly safe to use statistical machine learning, which is precisely when whatever the output of the machine learning model tells you, whether it's right or wrong, doesn't matter for safety. And typically, if you're searching through a search space for something, and you use AI to highlight, as a torchlight, saying, "Hey, look at this area of the search space. Could be right, could be wrong." It doesn't really matter if the solver doesn't find a solution there. Then you move on to another area. So as long as you use AI to produce outputs whose correctness doesn't impact whatever you want to show at the end of the day, then it's perfectly safe, of course, to use AI. I mean, this is kind of the heuristic, or using AI for heuristics kind of thing. So, but unfortunately, there are many other applications of AI in which that's not the case. So the question is what to do there, and I think that the work that you're doing, you and Lucas' team, and is very important there. But the answer is not so clear cut. I mean, clearly, if AI is just there to boost efficiency, to cut down search times, etc., this is a very safe and good use of AI. But there are many more challenging questions outside of that framework.
Yeah, I just want to add something a bit lateral to that, which is if you go to a machine learning conference or you talk a lot with machine learning people, they have dreams. And I disagree with these dreams, but they have it, and since they receive a lot of funding, you can't stop them. And so the dreams they have comes really from the connectivist tradition of a lot of philosophy, even linguistics. The idea that, well, our brain must be working in some ways. We are able to do logical reasoning and produce symbols. So why should a neural network not be able to do that, right? So that's their dream. And there's people who are true believers, who it becomes almost like a religion. They say, we'll make bigger and bigger neural networks, and then at some point we'll achieve artificial general intelligence or something similar. So we have now a completely black box AI system like our brain that is able to produce symbols and being as good as a human. They'll be working on that in the next decades. Who knows if we'll ever achieve something. But then it's very interesting, the point you were making is that even if you imagine that you have a neural network that is as good as a human brain, how do you deal with the responsibility? Because in the end, if there are mistakes that happens and an engineer made a mistake, it's that engineer's fault. If this machine that is executing a neural network made a mistake, whose is the fault, right? And so there's a bit of a lot of philosophical discussions. I haven't been to a workshop that was dedicated to discussing responsibility of AI systems. But so basically what will happen is that we have engineers doing good machine learning system, and what they create is a philosophical problem that maybe is beyond us, right? But yeah, that's gonna happen.
I can complement what you say. Yeah, just to complete what he said. Yeah, you have a problem of responsibility. So we've been involved in the autonomous shuttle for years. And this is the first question that is asked. Who is responsible? Not the shuttle, the car manufacturer, because he's not in charge of things. Not the driver, because the car is driving by itself. And not the insurance company, because the insurance company don't want to pay for the risks they have not created. And what is really interesting is that a lot of people in the US are following Tesla and what Elon Musk says. It's Jesus Christ, okay? And so they are very good at marketing, meaning that people think that what Elon Musk says is correct. And so there was recently there was a case. So one guy died in his Tesla in a scenario that is similar to one advertisement, one video published by Tesla. And Tesla is in trouble because the judge say, okay, the video represents the scenario in which the guy died. Elon Musk publicly admitted that the car is safe and you can sleep in it. the information that your car is not safe is hidden inside the user documentation. And so Tesla is in trouble. But for the time being, so there were a number of people being killed by Tesla cars until now. And in July, you've got the first US American who was condemned to go to jail because he was supposed to be in charge of the car and is fully responsible for the thing. So at the moment, it's a driver in the US. In Europe, you can't have a car driving by itself. The only one, so the most advanced car manufacturer in the world is Volvo. And so they have managed to reach the level 3. So 5 is the maximum. It's the car is just say, I want to go to point B, and the car goes to point B. And they are at level 3, but only when all the cars are going the same direction and when the speed is below 50 kilometers per hour, because the risk is limited. So the main risk is when we have crossing lanes and high speed. So at the moment, yeah, the responsibility is a subject.
I think Arthur wants to share.
I'm conscious of the time. I think we should be wrapping up. But just to say, even if we avoid the discussion around AGI and stick to the current systems, which are not there yet, I can tell you, although some have those dreams, like it was mentioned. And the regulatory frameworks will have to be developed, right? We will see that playing out in the next few months and years, and clearly the responsibility will have to be shifted, and this is going to be a major development. The European Union AI Act, Biden's executive order, the UK's AI Safety Institute and stuff like that. So all of that is, exciting, challenging, risky at the same time. I don't think it's existential, at least for now. But just to go back to the research and the question of one thing that surprised me, maybe it surprised you as well, is this idea of specifying code with natural language. I was told when I was studying software engineering, I was told that we needed to have a specification that was not ambiguous, right? And here we are now looking at these systems doing this. So it's very surprising that this is happening, to me at least. And the way I like to think of it is in terms of changes of representation. Not so much that there is a fundamental difference between one approach and another within AI, but that forms of representation are being used which are different, distributed, as opposed to descriptions which are symbolic, and we have to make sense of it. But I'll stop here. Thank you.
Thank you, Arthur. I think there's a question. I think we can end with this one.
Thanks. Actually, what is this? I need to both?
Just for Arthur to read.
Oh, okay. Yeah, actually, I was going just to comment on Eduardo's idea. I'm sorry, I'm going to disagree on it because I don't think it's a philosophical problem anymore. Like the cars, the Tesla cars, it's a real problem. Culpability and how we regulate that. And we have several examples today. As a very simple one is we have AI agents reading CVs now, right? So we put people's lives and careers on the hand of AI. And are we okay with that? And I think a lot of people are not okay, but also we don't see a huge movement to regulate this stuff from the companies that create these AI agents. This year, I saw the news. I think it was Google Brain that just they had this layoff and they just cut out the whole team. That was like the safety for AI models. And when we have these layoffs, those are the first team to go. And it's not a philosophical problem anymore because we see these problems, we see biases, and it's really sad that these companies are investing so much money in creating these AIs, but not on dealing with the drawbacks that they bring to our society as well.
It's quite controversial. And yeah, do you want to?
Okay, so let the fight begin. So I just want to qualify, when I say philosophical, I don't mean an important abstract thing, but I mean philosophical in a technical term, in the sense that it's not anymore a discussion on formal methods or AI. It becomes a discussion where you need to have a lawyer in the room, an ethics professor in the room, a business professor in the room. Like it becomes policy, it becomes a discussion that is way beyond us, and we're probably not qualified to have it unless some of us has a degree in those fields, right? That's my point. But it's a discussion, yes, will be more and more prominent. It's just bigger than me for sure, and probably bigger than us.
Yeah, just a quick reaction. Being the devil's advocate and also being based in the United States, we deal with everything with money, right? So we could also turn this into a financial problem. Why are we not more bothered about responsibility in the current situation before we use AI? I mean, Thierry, you were talking about a certification process. There's somebody that looks at how this system has been developed and puts their signature there. So that somebody who's, happy enough with the level of, with the confidence that they could analyze, that they can put their job on the line with that signature. Well, maybe at some point AI systems will become, will provide enough, maybe at some point there'll be somebody who's convinced enough that the AI system, that the machine learning model does a good enough job that they're willing to put their job on the line to put their signature on it, and that's the person who's going to be responsible. So, you could turn that into a financial problem. Like at some point, if AI systems are becoming good enough, maybe some people are willing to actually, be paid every month to put signatures here and there and be happy with that. I'm not saying it's my opinion. I'm just saying, I'm just throwing an idea out there. Being,
Just a quick response to that. I don't think it's at some point. I think it's already now, or maybe it's already happened. So, but in this sense, CEOs of companies will become convinced that you can replace, let's say, programmers with ChatGPT, will fire people. Then, after a few years, their company will collapse. But then it's their problem as a CEO. They made bad financial decisions, they made the company collapse. In the meantime, those programmers lost their job, and it's awful for them. But yeah, then becomes a discussion of capitalism, which is again philosophy, and I am not qualified to have it.
Okay, I think we need to end. It's a very interesting topic. We could go for hours discussing that, of course. But we can go and proceed to the coffee break and continue there. Let's thank the panelists once more, please. And just so we have the coffee break now, and after the coffee break we have the business meeting, which is a meeting to discuss organizational aspects of the conference and the future and so on. And everybody's welcome, but just to let you know, we don't have that much research wise topics there, and just some more organizational, and it will be held in Portuguese, so but everybody's welcome to come, and thank you all, including Arthur there. See you tomorrow. We're looking forward to your talk tomorrow.